I'm in room 142-033. And we were struggling to get the Zoom meeting started, but I emailed your team yesterday to us to set it up, and it just started now. So I guess it was taken care of. So I'm gonna. Yeah, we're having a few issues, and we're having a workshop starting at 8. And I was wondering if you could send someone from your team here to help us in person, if possible. Getting the presentation on the laptop to show up on the screen.
Oh, people are up in Cairns.
Yes. And they see it.
Yeah, if you can do it from there, that would be awesome. We attach the laptop to the HDMI cable that will be provisionally attached to the computer in the room.
Hello, Cairns. Can you hear us?
Yes, we can hear.
Okay, cool.
Okay.
So it is on.
Yeah, it is on.
Yes, we can hear.
You can see us? Yeah.
You can.
Yeah, there are two cameras. So.
I'm confused. This is the camera.
No.
Right.
And also.
Hi.
Matt.
Can you hear us?
I can see you. Yeah, I can see and hear you.
Yeah, we're trying to install the.
Yeah, no worries. Thank you.
Yeah, we're just trying to put the presentation on, but it's good to know that the Zoom is working because we were worried about that.
Yeah.
Oh, it's a start. Don't speak too soon though. We'll see how the presentation goes.
It will. My God, Jacob.
No, it wasn't working in here yesterday. That's why I said inside joke, I guess.
It seems to be very, very good for us here now.
Oh man, that's not it.
Yeah. Sorry that you guys have to go through this.
It's always more fun. They never answer my emails, but they set it up, so that's good, I guess.
And that's the thing, so what's the problem in saying, okay, it's all set up? They don't say anything and they set up. So you are completely in the dark.
I got trapped in a loop. I learned that I thought let's be fun here. What can you find? Like all the people that are coming here, I think, oh my God. And so I went, I did that door. And they did that, another parking behind.
This is
It's for you. Everyone can be choose.
I think there is which one you want. Oh, there's your
Oh, we can
computer.
see your.
oh, perfect.
Can they see?
Can they see
They
this?
have.
Now I change the camera.
And
At least one thing is that I wanted that camera on because I think I'm gonna be presenting mostly from here. I think my computer's gonna be there. Gonna be weird.
I can change the 300 lights.
Nope. No, it's only the photo.
Oh. Hold on. What?
How did you do it?
I don't know what happened. You did it.
Okay, I changed this.
So, oh,
there you go.
Yeah.
This is the one. connect to the VGC to the HDMI.
I think that,
Or let's connect laptop, blah, blah, blah.
You can connect your laptop wirelessly if you want to, or those instructions.
Oh, maybe that's a good solution. Because then I can have my
Yeah.
laptop there. That's true.
Good morning.
Morning.
Do you recommend setting the site or?
Yeah.
Oh, yeah.
Okay.
okay.
No. I just need it.
I cannot,
I just run the computer.
I cannot see it. I can only see the phones. That's gonna be done.
If I press this.
No, I think there is only including the other VGC room because they both full, so then it's updated.
Bogna, you must be smarter than us because you found the room faster.
I think
I'll sit here next to you. I like it. We can do this together.
You don't stop it.
I thought the meetings are really not to do anything that tinker around.
Oh, yeah, I'm intentando.
I used R a little while back, so I was kind of play around with using these regression trees, but it didn't work for my analysis I was trying to do, so I gave up.
It's there, there's one there, but we sort of, so I don't know if the ball is faster.
So that's the only way. Yeah, we're trying to figure out how.
Yeah, it depends how long your cord is.
How are you?
Good thing for you.
Yeah, my laptop.
Oh, at least two.
Oh, yeah, there's gonna be some on there too. Okay.
Only one person. Only one person.
Oh,
You want
I
it?
thought you were connected to a stupid adapter. Yeah, can you put mine in? It's a little finicky. You have to tinker, when you see the lights blink or the lights on, then you know it's working. It has like a green and orange light that will blink on. Oh man, you're making it worse.
I'm making it work. You don't have.
I'll do it. Yeah, this thing comes off because it has detachable endings on it, so that I can put a different one on for different countries. So I have to push this thing back in. And then
The problem is you didn't.
make sure it doesn't come out when I put it.
Connect there, right?
There we go.
Fantastic.
I need to just get a computer plug that doesn't have to use an adapter. I got around to it.
Where do you want that to
I'm
go?
trying to like sneak it around here. So it won't be good.
So you cannot see Jacob behind me. You
I got my new app building access card.
Oh.
It's the same as my old one. They lied, it wasn't connected.
So they're not connected.
It's just this.
This connection is room to room, it's not through the Zoom.
I don't know, just gave this to me.
Which,
That's all they
that's
had
why
lying
I'm
around.
yesterday asking them to fix this.
They didn't give me
because
this
every
cool lanyard,
conference
so.
We have this
That's
issue in that room there. You need video conferencing. to
Now I
link
won't
the
lose
two.
my cards ever.
Yeah.
Okay.
Why didn't you like my healthy cereal choice? 6 vitamins. It's not 6 vitamins like
Now, what
and
was,
minerals, it's 6 vitamins and 6.
now what was the first ingredient of the cereal?
I'll have to
Was it refined sugar?
It's probably like wheat.
It's probably something like puffed wheat or rice, and then second ingredient sugar.
But it didn't have
Pick a spot. The number one canned coffee in Japan?
Yeah.
My number one coffee for my coffee pot.
No. No, it's fine. I don't make coffee.
I'm making coffee myself and picking a nice special brew. It smells like a caramel hazelnut flavored brew. I guess I should open the car. I already have all the packages. I didn't check. But it's like
Maybe
in
you
my
tell them there's students.
pocket. Oh, I'm not connected. I like to use our. I like how our studio kind of automates the code for you if you're typing. Oh, try to autocorrect your code. Hi guys. I'm Jalen. Sandra. And who are you over there? All right, the table's officially.
Yes.
Okay.
Don't stop at times, and then just bring this to me again.
And all we have to do is struggle together.
For the presenter.
Yeah, right, I'm coming at it with the wrong mindset. No, it will not, there's no quality on this.
And I don't know if I can do it.
I don't know what happened, it just, my icons got really big one day and I didn't know how to shrink them. I don't know why that happened.
What? Ah, lovely.
It was so such a big I tried one, and it was difficult to resolve, so I just decided.
What is going on? What is
That happened about 6 months ago.
What kind of start?
Here's my autism.
And repetition.
This computer got me all the way through my master's.
Yeah.
Except some days like this, it's just
Repetition, that's exciting.
Yeah, so I think especially in the rap, I think
yeah, what's that thing? Fancy. Yeah. Look at all of us sitting here without one of those.
I have
Very heavy.
Well, yeah, yeah.
I didn't see what exactly.
Yeah.
This room is so awful. We
I
can link
see.
to the QR code.
But I mean,
that's sends it
I
on
didn't-
I don't know
Oh, really?
Really fun. Yeah.
And the
Especially with art.
Everyone installed everything.
Are those
Okay.
might not
The
work
people are-
for customers who remove the map?
Have you turned it off?
That was a problem.
How do I know that?
Oh, see, okay.
Yeah.
What is it?
This is my first on-campus workshop ever, not on Zoom.
How does it feel?
Thank you.
It feels pretty good.
Yeah, it's not
It's more interactive. It's not like me sitting in my room by myself while my ferrets are playing around, waiting to do a workshop. Or me laying in my bed, ready to do a workshop. I did lots of workshops lying in my bed.
There you go. But now this is.
I don't know, I'm a.
Stay there.
I don't like.
Same.
Oh, I did all kinds of work, like curled up in my bed.
You're gonna use your brain, it's gonna associate with that stress, and then you're gonna get nice. I don't get it.
I haven't been getting very many lately. Not a hundred.
I don't think so.
I started stingers for my PhD. Maybe I can learn how to map their distribution patterns using numbers, therefore I'm here.
Local adaptation.
There's clearly something you still gotta find a Python. Yeah, always.
Look what I've been making. These are all my results for chapter 2. And I want you to see some of my pretty graphs. Yeah. That, I'm using overview by side. This is a macro transect pad. There's like a pie chart. And then transect paths of like where rays are located within the path. I made more pie chart. That was a kind of. I was mapping ray density over tides. I like I was looking at ray behaviors and percentages of each behavior, like over different tides and along different bank tides, how far they go from the edges, things like that.
I don't know why students
Kind of showing like where's the behavior. Then I compare behavior between rays and clusters, rays and sizes of rain clusters, where they were located, and then all everything else.
Don't tell
And what
anyone.
I want to- That seems like something really good practice because I need to know what I want to do with my other side. Like since this is all like my model side, so like making this big giant PowerPoint was really good for me to understand exactly what I have and what I would like want. I've been working on that for the past
People don't use the, we don't have it.
I don't know.
Yeah, you.
Probably
Just all they get
Cartesian. You just, put on an abnormal or something.
So I haven't had to give you yesterday was the first inspection. I was like, when am I going back?
You know what I
think they hired them. If they're too
I
nice,
did a
they
whole
don't.
bunch of.
Evil.
You just put them in a solution.
I
mean, put them in a multi-polygon solution. Now imagine if I put that.
Yeah, we do that for,
It feels that you're doing it.
so you can overdose.
You're doing it too.
So like,
Yeah.
put too much in, or if you do it like those. Yeah, then instead.
Yeah,
I'm
I'm
not
not
like
like
something that would measure the result.
It's still one for 2033. We tried 3 different computers and they all have the same issue.
I guess we
You
can
see the presentation for a second
We came back
on the
to-
screens and then wait a second on the screen.
Your day is not real.
It's a problem with the cable, I think.
What's your problem?
The cable is like broken to this actual, to connect the laptop to this screen. It like shows up for a second, then it goes green. There's no reason why.
Why do you need it connected?
Presenting for this laptop.
Oh,
I don't know if this you should speak with about this, but do you know another room that we could use instead if it's a room issue? We got 25.
Let's go to the strategy campus. Find a way that- It's 19 years, I'm like.
yeah, you're around more people if you come in this building.
That's not a problem.
You have to provide a relationship counseling for your fish.
But then they were saying, I'll put another one.
He just got one.
Apparently the time.
Yeah, we
So
tried
impatient,
3
I want to go out and do this, but Carlo and Trevor was like, oh, no, we got bad ties, can't do it.
Yeah, you don't want to be.
we're trying
They just don't want to talk about that.
That's why I was grilling them about it. I was like, Carlo, you pull up a tide chart, you show me exactly why these tides are no good. Like, show me why they're bad. Cause I was looking at the tide chart and I thought it was great.
Probably like Austin.
What's the
Yeah, I was a little impatient yesterday. So I'm like, I just want to go out and do this thing.
It's not like you've been waiting for over a year.
I've been sitting for over a year not doing field work. I want to go do field work. I want Kevin to just go with me tomorrow and watch me fly a drone for a while.
Yeah.
And then after he watches me like one more time,
Yeah.
then I'll be confident enough where I can just take a drone out of the lab and go myself. Yeah, like I would be perfectly happy if I could just borrow a drone and go like take it out and practice flying stuff on my own.
Look at
we
If I
tried
can't
after.
go and catch my stingrays
They want you to
until
be-
there's good tides, then I can just go out and become a better drone pilot. That's something I can do.
Last thing you did,
I don't put the.
From the HDMI to the USB.
To the house
after
they
you,
rented.
like if you come up with if you want to.
You have to- You have to fly to Brisbane to get the keys.
It's just
Back to the
more for a while. It's
I already have so many side hustles.
We just feel like you can now recognize
Not yet.
My side hustle from yesterday showed me that I should go into acting.
That's not a bad deal.
Yeah, the person who watched my VHF radio test said I did the best Mayday simulation call she's heard in 20 years.
Yeah, that.
I really put on my acting. I really acted like my engine room was on fire and we had to abandon ship. And
111.
I made up a location where we were at and she was like, that sounded so real.
to go from dying out.
Okay.
If everyone just made a call like that, then everyone would be rested down.
Yeah.
It's not my
We
job.
just throw out.
Is that for today?
2 hours of my time last few.
Yeah, I still didn't see like the packages or anything.
Yeah,
I tried to
I've
look
seen
at
it,
it, I wasn't sure
Yeah, okay.
in these
I'll
folders.
go there and check it and you.
If it was here.
Might as well.
Oh, I tried to
Yes.
open it on my desktop computer, but you have to open this hour, right?
Oh, yeah, that's good.
Like you want to download this file?
You do that and then run in the other room.
Okay.
Totally.
You open it.
Okay, well, I think we're so do you need the adapter? Because now we know it doesn't work.
Can you check your phone if it works, or send me a message?
Oh, I started. People in Cairns and Zoom Hello, Cairns. Cairns. Hello.
Give a thumbs up, I think.
Hello?
Can you hear us now?
Yeah, all good.
Nice. So we're having technical issues as expected. Sorry about that. I will get started. Well, good morning, everyone. And up in Cairns, and I think people through Zoom can also hear and see me.
So what are we doing?
Anyone at Zoom can just confirm that they can hear me. Is anyone connected to the Zoom? Are you?
I'm trying. Did not go.
Now we can see Lorenzo and Natalia up there. So, yeah, so just so everyone knows, we're trying to sort this out. We might need to move rooms, which is good because this feels a bit too, I don't know.
Quaint.
Yeah.
Yeah. Yes.
Okay.
Can you
Alex,
hear us?
here.
No?
Yeah.
Can they hear us? Can you
No,
hear
I
us?
told Kevin.
Like we're successful, so might as well
Huh?
just move to the other room now.
But if they cannot hear the.
This is the one upstairs,
I
right?
messaged them.
Okay.
111.
Yeah.
Yes.
You unplug it.
Yeah, unplug my weird converter thing. There we go. That comes apart.
Oh, if you have to restart, it's okay. I will do it.
Everybody.
Maybe. How do we turn the light on?
I don't know. I'll find. Oh, I know actually. Here.
Oh, you put your finger in there.
I know, it's such a great ally for it. I'm sorry, it's always. You're always so-
Yeah, I got the North Drag bag, North Face.
That's my phone.
Why I love you. I don't want to lose that.
Don't disconnect that laptop.
I just hope it works.
I think, yeah, I think it is working. Lorenzo is,
Yeah, okay, that's not this computer. That's over there.
yeah, they can come back in.
All right.
Thanks for having this like yesterday. I saw your email this morning.
Sorry about the delay, guys.
It's all good.
The wonders
These
of
things happen.
yeah, the wonders of this video conferencing. Sorry for
He's not, man. You always never give the first room.
Shit. Right, now we don't have a whiteboard.
Pardon me?
You can invite here. If you have a piece of paper.
What was the source
Yeah, I can figure this out. I think it's a demo camera. The right document. I think the whole thing is because we're using their source now. That was the problem. I mean, yeah. So I need a piece of paper to draw on this thing. Yeah. Can I use my fingers? I can find a piece of paper.
Can people on Zoom hear us?
Say one more thing.
Yeah, that's a
Ken
yes.
Ken says yes.
All good.
I don't know.
Thanks, Jacob, and for everybody else, sorry for the delay. We had some issues with Zoom, as you noticed, but we should be all set up now, and we got Ale giving us a very informative and interesting presentation about how to do maps in R. And I hope you're all ready and excited and full of enough caffeine to last 4 hours.
But the community, quick acknowledgement of country. We just like to acknowledge the Multi-Polygon Geometry and Bindle peoples of Townsville, and where I don't know hands on head over.
Yeah, thank you for the reminder, Kevin. As we are on Multi-Polygon and Bindle people here in Townsville, we would like to acknowledge them as the traditional owners of this land and acknowledge leaders past, present, and emerging, and the same for the Cairns land. I am unsure of the traditional owners there. Maybe if you want to say that, Jacob, that would be appreciated. Thank you.
So, Walumbra.
Loudness. That's India. Do we need a microphone?
Not to hear.
Honestly, I don't think we need the microphone.
Yeah, okay. I much prefer without a microphone. Whew. All right. We might as well get started. Well, sorry again for the technical issues. For the people who watched my pre-completion seminar knows I love Zoom. It always gives me great surprises. And today it's not different. If you want, I can tell you the story later, but maybe that's something for the future. But anyway, now we just need to figure out how to draw. Is this how it works? I don't have a whiteboard at the moment. Maybe it's that one. Oh. Ooh. Wow. Technology. Sometimes it works. Right. Cool. Well, for those who don't know me, my name is Alexandre Siqueira, or just call me Ale. I'm a postdoctoral fellow at the farm hub or the read function hub working with data build. And I do a little bit of mapping. I played around with it. That's not my specialty. So this is the first kind of disclaimer I have for you. Yeah, before we start. And I know a little bit of plotting, but in terms of mapping, I just want to make sure that we're on the same page from the start, because this is not a workshop about how to produce maps. This is a completely different area. This is a thing for cartographers, geographers, they do this kind of thing. This is a workshop about plotting maps in R, which is a completely different thing. And it's very handy for us. I assume most here are biologists, and we need to plot nice figures to put in our papers, and then that's it. That's what this workshop is about. And to start, I think the most important thing for us to learn, not only for maps, but for plots in general, you need to understand the basics of plotting. Once you do that, your life becomes easier and you have total freedom over your plots. It doesn't matter if it's a map, it doesn't matter if it's a phylogeny, which is something that I work with. It doesn't matter if it's, you know, just a normal scatter plot, bar plot. You just need to know exactly what it entails to generate a plot in R. So I'm going to start from the very, very basic. And some of you might think, oh, this is super basic. I know this. But I want you to get that mindset into when you're plotting things in R. That gives you total freedom to plot anything you want, right? So let's think about what a plot is. Essentially, you're trying to, most things in R, you're going to be trying to plot something in two-dimensional space, right? You're going to try to represent something, whatever that is. And usually, you need a plotting area, right? R starts with a plotting area, just like Illustrator and any other plotting devices that you can use. So essentially, you have two axes, right? You have an x-axis and a y-axis. So if you are just doing a normal scatter plot of points along this two-dimensional space, or you can call this a Cartesian plane, because a Cartesian plane is this one that you have x and y axis. And let's say your axes go from 0 to 5, going 1, 2, 3, 4, and the same for the y-axis from 0 to 5, 4, 3, 2, 1. Never mind the terrible handwriting. If you want to plot a point in this graph, all you need to know is the coordinates, right? So coordinates is another keyword for us. So let's say you want to plot a point that has an x value of 5 and a y value of 5. Where would that point go? That point would be where 5 in the y-axis meets 5 in the x-axis. That's very trivial, I know, but think about it when you're plotting stuff in R. All you need to do in R is to give it the commands to do this exact function. R does exactly what you tell it to do. So now, because we are in a workshop about maps, let's change slightly our thinking. Let's have, again, our x and y axis. Hope you guys can see it. And instead of having these axes ranging from 0 to 5, we can put the 0 on the x-axis in the middle and make it range from minus 180 to plus 180. And in the y-axis, just make it range from 0 in the middle to, let's say, plus 90 and minus 90, and all the values in between. How about we call this x-axis longitude? How about we call the y-axis latitude? There you go, you have your map. As easy as that, because when you're plotting maps in R, this is all you need to know. As you can see throughout the morning, it's not as easy as that. But if you use this thinking, you're going to be able to plot anything you want in your maps. So let's say your study site was right where the Greenwich line meets the equator. So you have a point here. 0, 0. Right? I think that makes sense for everybody, and this is pretty straightforward. And this is where I like to start. Just for you guys to know what we'll be doing throughout this morning, right? So now let's do this in R. Why not? As easy as that. So we can turn this off and go back to the computer. Oh, laptop, not computer, laptop. Cool. First of all, I hope you all have installed the packages that we need for this morning. Has anyone had any trouble? No?
There's one problem with the Terra package, that the version says they require a new version, but the version is not available online. I don't know if we need it.
Okay, we can check that out. If we get into trouble, we can check that out later for you. But hopefully there shouldn't be any problems installing these packages. They are pretty basic packages for plotting maps in R. But I forgot to say at the beginning, like, you can interrupt me at any time. Feel free to ask questions. Feel free to leave, go to the toilet. I don't mind. I'll be here talking, interacting with you, and you feel free to do whatever you want. Okay, cool. So let's do that very simple exercise to start with.
Do you mind making the text a tad bigger? Possible. Like common.
Yeah. Did it help?
Yeah, that's good. Thank you.
Cool. Let's start from the beginning. Basic plotting in R. First thing we need to do, as you will notice, I won't load any packages in R to do this first bit, because all of the basic plotting functions are already native to R. So if you want to do very basic plots, you don't even need to load any packages, any Ggplot or anything. And honestly, I do recommend, if you are going to transition to Ggplot, and if you think that Ggplot is very overwhelming, start from base R. Understand the basics of plotting, then go to Ggplot, because then you will know the different. It's just a different language sort of thing. It's the same language, it's R, but it uses a different kind of environment, right? But the concepts are the same. Okay, so we start by just opening an empty plot. This is our Cartesian coordinate plane that has X and Y axis. So we can do that. We can plot, for example, like I said in the, like I draw for you, in the example, an axis that goes from 0 to 10,
in the x-axis and from 0 to 10 on the y-axis. And then you can give it labels, x label, y label, and give it a title. This is your plot. Now let's say you want to, like I said, plot a point in x equals 5, y equals 5. It's as easy as this next line of code. And then there are other arguments like PCH that defines the aesthetics of your point, and the CEX, which is the size of your point. And then you can do the same, but plotting x and y 10, and then 0, 0, and there you go, as easy as that. And you can do the same. You can unite those points by using lines. So in the case of lines, you gotta give it where it's going from in terms of the x-axis and where it's going to in terms of the y-axis. So this line is going from 0 on the x-axis to 5 on the x-axis, and from 0 to 5 on the y-axis. Same thing if you want to unite this other points, right? So pretty simple, pretty straightforward. But if you've never played with plotting in R, you might think that, oh, plotting something is very overwhelming, but actually this is exactly what it is. It's just small lines of code, and especially when you get those pre-made functions. Let's say you ran a model and you want to plot a PCA, and then there's a pre-made function to generate a PCA. You don't know what the hell it's doing in the back of that function. What it's doing is just simple steps like that to plot your points along a Cartesian coordinate. The PCA is nothing but a Cartesian coordinate that calculates the Euclidean distance between the points, and that's and displays that on a two-dimensional form, because you're trying to reduce the complexity of your data. You have too many axes of variation. You're trying to reduce that into the two axes that explain most of the variability. That's a PCA. Right. Now, let's do the same thing that I did before. So let's change some basic settings. Let's create an x-axis that goes from minus 180 to plus 180, and a y-axis that goes from minus 90 to plus 90. Let's open up a new plot again, and let's plot all of that. So you can add the axes, telling them exactly where the ticks of the axis are, and the same thing for the y-axis. And then why not? Let's call it longitude, the x-axis, and latitude, the y-axis. And let's call it map. Right, you want to plot a point in your map, as easy as the same thing we did before, just points along x and y coordinates, and lines again along what x and y coordinates, and that's it. As simple as that. There's something missing on that map, obviously, but if you use this way of thinking, because the most basic map plotting functions in R, the default maps, they come on a two-dimensional axis that shows latitude and longitude as x and y coordinates. So it's a straight grid. So if you want to plot a point in an actual map using the default functions, you can do, it's as simple as that. And that's what we're gonna do right now. Okay, now let's start really plotting maps. So this was just an exercise so you could understand what's happening in the background of these more complex functions in R. Right, okay, so just a quick run through Ggplot as well. So we're gonna do the exact same exercise that we did, this basic plotting exercise, but now using Ggplot. So I'm assuming as well that most of you are also familiar with Ggplot. You all love Ggplot because it produces nice graphs from the start. And that's a big advantage of Ggplot indeed. But I'm telling you,
transition to Ggplot after you've understood basic plotting in R. Because Ggplot is full of these pre-made functions that you don't know what's doing in the background. And then you just, if you want to be free to modify simple aspects on your graph, you won't know how to do it. So, and using base R is much easier to modify those simple things that you want to modify in your graph. Right, so let's use Ggplot. So now let's load our first library. And then plot the same thing, but using Ggplot. As you can see, I've already went the step further and I plotted our map, but now using all the lines of code that do exactly the same thing that we did in base R, but now using Ggplot, right? And you will understand that the geom point in Ggplot is the same as points in base R. And then you do the same thing, you give it the aesthetics, AES, that tells X and Y coordinates. So it's the same thing, the exact same thing. And then you give it a size. So that's why it differs slightly on the arguments that you're giving, but what it's doing, it's the exact same thing. But why people love Ggplot is because it has these preloaded themes that make your graph look good from the start, which is fair enough. And today, most of the morning, we're going to be using Ggplot. Indeed, Ggplot is much better for plotting math stuff. Point for you, Kevin. Cool. Right. So let's get into real maps. Now we load our first library, which is the most basic library for plotting maps in R, which is called maps. Brilliant. And plotting a world map is as easy as this line of code. You can almost ignore all of these other arguments that I'm giving it, except the y lim that I'm defining the limits on my latitudinal coordinates. I just wanted to expand this a bit because usually it goes from -90 to +90. I just set it to go from -95 to +95. And then you just plot using the function map. And then you have a world map. Maps, this first library, uses the functionalities of base plot, base R plotting. So if this is a base plot map, we can do the same things that we did with the base plot Cartesian coordinate. We can put axes in it, telling where the longitude points and latitude points are. It works as simple as that. Do you want to give it the labels? Let's call it longitude and latitude. Let's give it a title, my map. Wow, now you have a map, an actual map. You want a point that crosses the equator and greenish line. There you go, that's your point. You want another point that crosses an unexistent area in your plotting space in the actual world map, but you can't because this graph goes from +180 to +90, which actually doesn't exist. When you get to 90 degrees latitude, that's where everything ends. But for the exercise of this today, because this is a plot, I'm just showing you can be free to play around with it. You can do whatever you want. And then plot another point here, and you can plot the lines the same way as you did before. There you go. As easy as that, using the same functionalities that we used before, right? Again, I know this is trivial for most of you, but like honestly, thinking first principles, it's what got me into being free to plot whatever I want in R. And I think that's super important. And sometimes we jump that step when we're learning R. And this is actually the most important thing to know. Okay.
Sorry, question.
Yes.
What's the standard projected coordinate system for this?
Good question. So we're gonna get to projections in a minute. And the reason why I didn't mention this yet is because it makes this whole concept of X and Y axis a lot more complex. And remember, I kind of already hinted on what is the default projection when I said that the basic projection projects a map and into X and Y coordinates in which each latitude and longitude point corresponds to an X and Y coordinate. So it projects it in a Cartesian coordinate. And the problem with that and map projections in general is because every projection has distortions in the actual map. So this map is distorted, just like every map that you're going to see plotted in a two-dimension plotting area. But that's a subject for the next script. But good question. Cool. Okay, now I have a very easy challenge for you guys. Now that you know how to plot a very simple map, plot a point showing where Townsville is in this world map using the maps library. It should take you approximately 20 seconds to do this.
Okay.
Just kidding. The hint is that Google Maps gives you longitude and latitude coordinates. And this is not a competition. This helps make it a little less dark. Lecture mode. That's where we are now. What about video mode? Yeah, that's better. Yeah, and that's good. Is everyone there? Everyone has Townsville in their maps?
More time.
More time. We got a Townsville.
Oh no, my time goes up.
No, it's too high.
Too high, okay. Remember, you can modify the size of the point if you're not happy with Townsville being so big.
Why is my time so low?
Yeah, it seems like
That's climate change. You're already projecting what's going to happen in the future.
There must be a typo.
Good call. Ah, there you go. Lorenzo, don't eat them. Sorry, so don't forget.
Oh, do you have to put the direction after the degrees, like the south and the east?
Nope.
No?
Remember how, think about the plotting. It goes from minus 180 to plus 180, from minus 90 to plus 90. So what would it be your west? Let's say you're in Greenwich. So everything that is to the right of Greenwich would be positive.
Well, maybe the coordinates that I will set here.
Maybe you switch where you put X and Y.
X is going to be the long end.
Yeah.
So that would be the long end.
It doesn't need to be a precise. Oh, no, I know where you're going. Now think about the y-axis. Think about north and south.
Oh, okay. I got it.
Got it? Cool. You got it down for us?
Oh. Well, Google can't assume that I know it. I got it.
Getting there, no worries. Take your time. Nice. Oh, wow. Circle. Oh, yeah. Okay. Sorry, people in Cairns and Zoom. I'm walking around the room now, just checking if people did the right thing. Let me know if you want to see me more, or if I'm pointing at something and you can't see it, please let me know. I'll try to use my pointer now. Is that okay? Cool. Can you hear me okay? Amazing. So, have we got Townsville, everyone? Next challenge. Oh, yeah, okay. For this one, you need to know where the E-specific barrier is. So, I want you to add a line to the map, the world map, showing where in this book chapter from 2002, David Bellwood and Peter Wainwright showed where the E-specific barrier is, number 2 there in the map. It doesn't need to be curved. It can be a straight line. Roughly where it is. Just plot a line there. And the reason why I have this challenge here is because when I originally developed this workshop, one of my students was going to work with biogeographic barriers. So this map is showing global biogeographic barriers for marine organisms, more specifically for reef fishes. And I wanted her to learn how to plot barriers on a map, as easy as plotting a line. So give me a line, give me this specific barrier, which, yes.
I was just wondering, how do you remove points from your map if you want to get rid of the other ones that we've done so far?
Just plot it in from the start. I'm not entirely sure. Is there? Do you know if there's a way of removing points? I think you need to start. You just start the plot.
Like use the line of code with the map.
Yes.
Starting there.
Mm-hmm.
Okay. Yeah. Blank.
Yes. Cool. I think that's the easiest way to go. There's probably a function that I don't know what to remove points.
I can add the axes back and then plot my one Townsville point.
Cool.
If I wanted to.
Yeah, exactly. Very good. I can see you're worried about aesthetics. That's very important. It's all about aesthetics. It's all about how your maps look like. It's all about the beauty of things.
Hey, Ale. People from Cairns mentioned that when you walked away from that area, they cannot hear you as well.
Right.
So maybe if you're saying something that's important to everybody, say it there. If not, we can try and set up the microphone.
Yeah. Sorry again, Cairns and Zoom. I'll try to speak a little bit louder when I move away from the microphone, which I don't know where it is. Here? Cool. Have we all got the E-specific barrier?
No.
Working on it.
Are we supposed to look up?
Yeah, roughly. And the position doesn't need to be precise. So you went, so you used 0.
Microphone check, still too loud.
So a line.
Microphone
X to X.
check now.
And Y to Y.
Hey, hello.
Yeah. So you probably got it right.
Yeah, the one between Australia and US we're trying to draw.
So Hello, hello. Woo. Hello, hello. Can you hear me now, everyone? Yep. Woo. Yeah. So yeah, remember that the line. So you have the first 2 points are x, and then the second. Yeah. Y. So where is it coming from? Where is it ending?
If you wanted to do a line that was like this, could you just have like multiple x points, multiple y points?
Yes.
Is that where it's supposed to be?
Yeah. That's roughly where it is. Well done.
When this is C and then the first.
Yeah.
bracket of numbers, is that the range of the longitudes, and then the next one's the range of the latitudes? Like this and this?
Mm-hmm.
Because if I was looking here on Google Earth and I wanted to put this coordinate in as like the start of my line,
Yeah.
would this be what I put in the first set of brackets?
Remember essentially what a line is. It is plotting from where the line starts until where the line ends. So you need to give it 2 x and y coordinates, right? Does that make sense? So that C function in R is called concatenate. So it is concatenating two things. And in that case, because the line, you need to give it a starting point and an ending point, you need to give it 2 x and y coordinates rather than 1. So when you're plotting 1 point, you just need 1 x and y. But for a line, you need 2 x and y's. That's why you have that concatenate.
So in each bracket, I have to put 2 longitudes, and then in the next one, 2 latitudes.
No, you need to, in each bracket, you need to put a longitude and latitude, and the other bracket, another longitude and latitude. Does that make sense?
Yeah, I guess.
Like you're plotting the 2 points and then you're just making a line.
Yeah, exactly. Think that you're plotting 2 points.
Right, so
One of the points you're going to put in the first C, in the first concatenate. The second point you're going to put in the other C.
Basically,
Sorry.
when I fill the numbers in, it'll be the x and y of this point. So that's-
Absolutely correct. Yeah.
So I'm just copying these.
How are you guys doing?
I got it. I was just trying to make like
That's probably not where I want to be.
a curve one.
That's okay. A curved one is a little bit harder. You need a mathematical function to define how it's going to curve.
Africa to
There you go. That's a very northeast specific there, but that's okay. I said roughly. I don't want precision. You're getting there. That's okay. No worries. It isn't doing anything.
Okay, yeah, this one's your fault. I have a negative 2.
That's
Yeah, that's the latitudinal range. That's the longitudinal range.
Well, look on your, if you draw the map. without the
Before
line.
I gave it one longitude, latitude, and then it did something over
Yep.
here.
How about negative 19 to negative 15? Does that sound like?
Look at your map in R.
I
without the line.
think you might have inverted
So here's the map here.
something.
Yeah, so
Isn't
So that's like that. From
-7,
down to.
but remember it starts on the x. So the first one should be the x and y, x and y. It's probably plotting outside the plotting area. That's why it's not doing anything. It's plotting somewhere in the plotting space that you can't see. That's close enough. Well done. Are you all good here installing the packages? Oh, I'm sorry. Yeah, let me know if you're not following or if you want me to go slower. Are you all good? Oh, you almost got it. This one is pretty close. So I said roughly. So we're good. Yeah.
We have a question from Zoom. Someone asked what the geom SF and chord SF functions are doing in here.
Right.
If you have an answer, go for it. If not, I can.
The question in Zoom, just letting you know, the reason why I'm going through a little bit fast this is because it's just the introductory part. I will explain exactly what chord SF is doing in the next script, if that's okay with you. Thank you for the question, and thanks, Lorenzo. Right, so did you guys get kind of the concept? So we're doing very basic plotting things in R that can be quite useful if you want to plot a line connecting a study site to another study site, a point showing your study site. So these are actually things that we use a lot when we're plotting maps. That's why I'm starting from here. Oh, sorry, that was my computer. My bad. People in Cairns, have we got an east-Pacific barrier?
We've got a barrier somewhere on the map.
Excellent. Well done. People in Zoom, have we got an east-Pacific barrier? You let me know, Lorenzo, if they are live.
Yeah, I got the yes from 215380.
Nice, thank you, 21850. Cool. Are we all good to move on? All good here? Yeah, got there in the end? Understood the concept of a line? X and Y and X and Y again? Lovely, well done. That's what I want. I want freedom. I want you to be free in your map and play around with it as if you were a kid drawing in a piece of paper. That's exactly what it is. That's what I want to give you, the choice. Excellent. Let's now move on. And this last bit is just using Ggplot. So using the same things. As I said, I will explain what geom SF and chord SF are doing, because these are going to be the most important functions for us today. And that's why I kept the explanation for them to the next script. So, okay, let's load Ggplot again. And we're going to load now two very important libraries. The first one is called SF. It stands for Simple Features. This is the most important package for mapping in R. Simple Features connects to a whole range of other mapping features outside R. And it has many important functions that we're going to be using throughout the workshop. And then this R Natural Earth is the package that is used to load a world map. So this R Natural Earth has a very nice world map. As we've seen, you can have a world map in base R using maps. So that gives you this most basic world map that we're looking at. But from now on, we're going to be mostly focusing on Ggplot and using these very important packages. So the first thing you need to do is to actually load the world map. And we're going to call this object world. And to do that, you use the function countries that comes from the package R natural earth. And here we define two arguments. The first one is the scale. So we're using a medium scale because we don't want too much resolution in our map for now, because a map can get pretty heavy. If you have all the coastlines draw perfectly, that map is really heavy, and you will understand why in a minute. So we just use a medium scale. That's enough to give us a good resolution of the world map. And we want it to return the class SF. The class of objects that we use to load our world map can be either SP or SF. That's probably irrelevant for you now, but SP is essentially the older version of SF. SF is a more advanced kind of way of storing the world map. And soon we're going to look at the structure of an SF, because that's very important for you to understand as well. Cool. And this other argument, I won't be getting too much into detail now. And I'm just turning something off. This SF use S2 equals false. This function is just turning something off because this S2, it's a new feature of the SF package that automatically switches geometries to spherical, and that creates all sorts of problems for us to plotting the axis, and all that X and Y coordinates just gets messed up. So now we just turn it off for the purpose of this exercise. And now we do the same thing, but using Ggplot. Just run that whole line of code there. Will essentially give you the same world map. So as you can already see, inside the geom SF, you're calling a data equals world. Remember, world is the object that we just loaded the world map. And you're giving it other aesthetic arguments, just essentially a color, a fill. Okay, I will explain this now. So essentially the fill color is the one that defines the color of the polygons. So now we're starting to understand a little bit of what a world map is in R. It is essentially a group of polygons that defines the countries. Each country in the world map is a polygon. A polygon is a combination of points in a Cartesian coordinate that gives you a polygon. So essentially, Australia in this map is a polygon within the world object. So if you want to define the color of these polygons, you use the argument fill. So we're filling it up with one color that I gave it the code #333, which is a color that I like because it's not black, but it's a kind grayish black. And the next argument, which is col equals transparent, gives you the borders, because each polygon also comes with borders. If you want to make these borders very large, you can. I don't like them very large, so I just call them transparent. So what you're seeing here is actually the absence of borders. But then because the borders are there, because the polygons are not exactly on top of each other, you can kind of see the white lines between them.
Also, the border that we can see between the countries is not in that code. You know what I mean? It's you can see the borders between countries.
Yeah.
This is into this code.
That's a very good question. It is inside the world object, and you're gonna understand this in a minute.
All right.
So keep that question. We're gonna get to that in just a minute. But to kind of give you an answer, for example, you could filter just Australia in that and plot just Australia. you could filter because, okay, a subject for the third script. Cool stuff. Now, the challenge begins again. Show me where Townsville is, but now using Ggplot, and show me where the E-specific barrier is, but using Ggplot. Should be, now you have all the coordinates. Now you have everything. You know how to plot a point in Ggplot. You have 10 seconds for that. Sorry, I can't hear you. Oh, really? When you load the library, it aborts R.
Maybe I have to update that. I don't know if anybody else is.
Can I see your R? Oh, yeah, I need to see the version of R that you're using. Can you just scroll up here, please? Just scroll up in the working space. No. Yeah, 4.0.2. Problem is, you might need to update R.
Okay.
Because, can you scroll down now? What it's telling you is that the package, oh, you're having the problem with RCPP. Maybe Kevin can help with that. Actually, you might not, you don't need to reinstall R, but Kevin. If anybody else, now Zoom and Cairns included, had any trouble installing the SF package and it's returning you an error message that mentions something about RCPP, that's a problem. No, just kidding. That's easy to solve, but let us know and we'll help with that. Because essentially, RCPP is a dependency of SF. So SF needs RCPP inside it. And RCPP is a C++ coder inside R. And once, if you have a Mac, especially, Mac has some trouble with C++, depending on what reader of C++ you have installed on your Mac. And that should be easy to solve. Just let us know and we'll give you a hand. Lorenzo knows exactly what to do. How are we going with the Ggplot? Did we get there? Cairns, do we have a beautiful Ggplot showing Townsville? I assume yes. Yep. Oh, yeah, that's a good question. I'm sorry if I didn't explain this earlier because I'm just assuming you guys are familiar with Ggplot, but essentially you just need to add it to the, as you can see, every line of code here, it's added to the other. That's something that's unique to Ggplot. So you just add a plus sign after it. You can add this line of code in the middle here, and then a plus, because then it's going to read. Essentially, what Ggplot does, it's similar to piping. I don't know if you've ever came across that. So yeah, what Ggplot does is like you call Ggplot, and then it opens an empty plotting area. And then, oh, I want Ggplot to open a plotting area, but I want Ggplot to plot this thing that I'm calling the data world. But I also wanted to do this. I also wanted to do this. I also wanted to, and that's the cool thing about Ggplot. You just, you know, it's additional. You just, and you can save the step by step as you go. But essentially, you just need to add it in there. Proven. Nice, 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 nice. Very good, very good, very good. You all mastered. Yeah, have we got an E-specific barrier? Cool. Did you figure out in the previous one what was wrong? It was the inverted. All good? Cool. Cool stuff, guys. Everyone, well done. You get your certificates. Well done. This is the workshop. No, just kidding. Yeah, right. Is everyone comfortable with what we've done so far? Any questions? Let's move on then. This was the first script. Now the second script, I would like you guys to pay a little bit more attention to what I'm saying rather than the code. This bit of coding is a bit, you don't need to know what it's doing. I just want you to plot these things to understand some concepts here. I've told you, I spent the last hour telling you how easy it is to plot something in X and Y coordinates and using a map, right? But things are not as easy as that. And the reason for that is exactly, it's a matter of geometry. And as Ricardo asked me already about map projections, this is very important because essentially, no one else other than the flat earthers denies the fact that the Earth is round or spherical, or it has a shape that is three-dimensional. So how do you get that three-dimensionality of the world and plot it into 2 dimensions? It doesn't matter what you do, it doesn't matter what kind of mathematical craziness you do, you are gonna have distortions in your map. So things that we're plotting in this very basic map, they have distortions in terms of the distances, they have distortions in terms of the area that the continents actually represent in real world. So these are all issues that cartographers have been trying to deal with for a very long time. So now I'm gonna quickly explain the problems with all of that. So you can run all this first bit of code until you get to this figure before the ellipsoidal coordinates. So what this figure is showing is, again, the same concept of a Cartesian plane. If you have a Cartesian plane, now focus only on the blue lines, you know exactly how to plot a point that goes from x equals 3 to y equals 4. So if you want to know the position of this point in a Cartesian plane, it's very easy to figure out, right? You just need x and y coordinates. Now, if you have another kind of plane that is not necessarily Cartesian, that is still 2-dimensional, for example, this polar coordinate system, this circle here is called a polar coordinate system. For you to know where that point is along that polar coordinate system, you need x and y do not suffice in this case. You need to know what's the radius of this circle. In that case, we know because it's equals 5, right? The radius is half of the circumference of the polar coordinate. And you need to know the value of this angle here. Then you will be able, or this phi signal, then you will know where that point lies along that circumference. Right, okay, these are 2 examples of different coordinate systems. However, as I mentioned, now you can run the rest of the code until you get to this point here, which is illustrating exactly what I just mentioned. So try to get your brain to think now three-dimensionally. It just adds more complexity. And if you have a sphere, and that sphere it's perfect, you can have what's called a Cartesian geocentric plane, in which for you to know where that blue point is in a Cartesian geocentric plane, all you need to know is how much did that point walk along the x-axis, how much did that point walk along the y-axis, and how much did that point walk along the z-axis. Then you know the position of that point along that three-dimensional space, right? It seems pretty straightforward at this point, but if you think about it, we need 3 different parameters to define the position of that point in space. Now, if you plot the next figure, you will see that cartographers came up with a very ingenious solution for the problem of finding the position of a point in a ellipsoidal coordinate system, which gets closer to what the Earth is when compared to a Cartesian geocentric point. And the way of doing it is by, within this ellipsoidal coordinate system, if you know theoretically where the center of the Earth is, you would know the radius of the Earth, depending on where you are. So you would only need 2 parameters to define a point in space. These parameters, sometimes called sigma or, lambda or phi, are also known as lambda equals longitude. So how much does that point move in, let's say, in a horizontal axis? And how much does that point move? So this angle, phi, is called latitude. You need longitude and latitude. And this is the basis for every geographic coordinate system. So if you have a GPS uses this sort of mathematical transformation. It requires a mathematical formula to calculate where the center of mass of the Earth is, and how do you calculate, given that the Earth is not a perfect sphere. So in this case, I'm illustrating a perfect sphere, but the Earth is not perfect. So the radius will also change according to where you are. So this just creates a lot of complexity to calculate positions on a geographic space. That's why GPS wasn't invented in the 18th century. It was invented very recently, and it's very well accepted these days as a way to find positions in geographic space. And the reason why I'm explaining this to you is because it's just to get you thinking a little bit more about what latitude and longitude really correspond to. It's actually very complex, but we can turn that into a simple concept if we're trying to plot it in 2-dimensional space, right? But have in mind, once we do that, we create all sorts of distortions. It's impossible to avoid the distortions when we plot it in 2-dimensional space. But honestly, this should not be a problem for any of you here if you're not a cartographer, if you're not navigating the world and you need to know the precise distance between points. That's not a problem for us, right? All we need to do is produce beautiful maps to impress the reviewers. And reviewers are not aware of how you calculate distances between points on Earth, I'm pretty sure, unless you are a geographer or cartographer, one of these people, right? So I'm just explaining the complexity here. But luckily for us, because the Earth is not a perfect sphere, making calculating distances between points very, very complex, R solves our problems again. There is a library in R called geosphere that has a function to calculate the distance between 2 points on Earth. So remember the map, the very basic map that we plotted in the first script. If you were to calculate that linear distance between the points that we plotted in the Cartesian plane, that would be so wrong. Can you visualize that? So wrong compared to the actual distance between those points. But to do that, all you need to do is to give this incredible package the coordinates of places in terms of X and Y, or longitude and latitude, and then it calculates the distance for us. Brilliant. And you don't need to know what mathematical or mathemagical functions it's doing in the background, unless you're very, very interested in that. So I did this exercise just as to illustrate my point by calculating the distance between Townsville, and then I put the coordinates here. What I'm doing now is just saving Townsville as an object that concatenates, again, using the C function of R here, a X and Y coordinate where Townsville is. And I also did the same thing for my hometown back in Brazil. First thing I want you to notice is crazy. Look at the latitude points of Townsville in my hometown. Crazy. I haven't noticed that until I did this. It's really, don't you think it's fascinating? I think it's fascinating. It's the exact same latitude. Crazy. Anyway, and then we can calculate the actual distance between Townsville and my hometown by using this function that it's called dist_Harversine, and from the geosphere package. And then I saved this in an object because this dist_Harversine function, what it does, we can call the help in R. Just if you don't know how to do this, this is very handy. Always ask R. Oh, what is dist_Harversine? And then it tells you. Harversine calculates the shortest distance between 2 points, the great circle distance, or as the crow flies, according to the Harversine method. This method assumes a spherical Earth, ignoring ellipsoidal effects. So it is telling you what the problem with this function is. But as you all are aware now, every function has a problem to calculate distances because we don't know the exact shape of the Earth. So you need mathematical functions to do that for you. And the same package gives you a different function because knowing that this Harversine gives you this much distortion in distance, you can choose, oh, how do I want to calculate the distances? Maybe using the dist_geo function is going to give me a more precise distance. And then you can ask, oh, what does dist_geo does? It gives you a highly accurate estimate of the shortest distance between 2 points on an ellipsoid default WGS84. I'll explain what that is in a minute. Ellipsoid. So the shortest path between 2 points on an ellipsoid is called geodesic. After reading these two, I know which one I prefer, because this WGS84 is essentially World Geodetic System 84. It was designed, it is the one that's used by the GPS today. So it's essentially a bunch of mathematical functions that define the shape of the Earth, the center of mass of the Earth, and all of that. So this geo seems to be like a more precise way of calculating distances between points, but you can, depending on your goal, you can use a different function, being aware of what the problems are. Anyway, calculated, and all you need to give to these two functions are the objects with X and Y coordinates that I created earlier. So I want to know the distance between Townsville and Belo Horizonte using these two functions, considering the Earth as a sphere, considering the Earth as an ellipsoid. And after you've done this, you can check this object, and it gives you the distance in meters. But I don't really want to know the distance in meters between here and my hometown because it's very far. It's on the other side of the world. So I just transformed it to kilometers because that makes a little bit more sense. And as you can see, from Townsville to my hometown, it takes 15,000 kilometers to get there. And more interestingly, you're going to see that the dist harvesting, the difference between dist harvesting and dist geo, it's 5 meters. 5 meters from one place on one side of the Earth to another in the other side of the Earth. Huh? 5 kilometers, sorry, thank you. Yeah, 5 kilometers. Honestly, that's not much of a difference. So that's why I'm saying, like, it really depends on your goals. If you don't want, and if you don't need to be as precise in calculating distances, it doesn't matter what function you really use. Like, it's not a 5 kilometers that distance that's gonna do any favors for me most of the times. If I was trying to calculate exactly the distance, then I would try to be as precise as possible. But on a comparative sense, if I want to compare the distance between here and my hometown and the distance between here and somewhere in Europe, doesn't matter so long as you use the same function, right? All understood? Great. Right. Do you guys want to take a break now, or should we move to the next script first, then we take a break? Now it's good. What? Now it's good a break, or now it's good?
Now it's a good break.
Cool. Is anyone got any questions?
I have an R problem.
Nice. Do you know the best way to learn R? It's just like walking. It's by running into issues and then trying to solve them. All right, so, okay, we're gonna sort out your issue, but everyone, I think, yeah, let's take a, say, 20-minute break.
Even less?
You choose.
Yeah, you should.
I would say even less.
Less? Okay.
No, I'm not saying. No, I mean, it's
15, yeah, 15.
15. We can finish before. It's good.
Yeah. No, that's fine. Yeah, up to you guys, and also let me know if I'm going too slow, too fast, too. 950 back here.
Okay, my problem is that I tried to install the latest version of R
Mhm.
because my last one, it's not doing anything with the Ggplot thing. It says it's outdated and it freezes and quits every time I try to run that code. So
Yeah,
I'm trying to
sorry about that.
put a new version on there, and I've installed the new version like 3 times, but I'm not sure how to open it. It says that it's installed like this. When I try to open R Studio, this is the old one, the one that I'm trying to not use. Yeah.
Which one is the version you want?
Well, I'm looking in my files. like,
Sorry.
after I finish the install, then I can't find the new version that I.
If you download a new version of R, and then you go back to
That's
Studio, it should
the
just be able to
one
restart
that
and it will go off the.
It should.
That's what I'm
Yeah.
Yeah, but then it aborted.
It aborts when you try to load a package.
So it was working after the new version of R, like the one was working, it's all good. And then
finished and
went to like do one more,
and then I look on my computer and it's
like
not
running
there.
it, and then it just aborted. And I was like, okay, I'll just chattel again. So that was
25
just like install a full version.
Oh.
That's
Think
right.
it went
I think
now?
it's there now. I think it should.
How come when I
Should be
open
fine.
R,
Yeah. Let me know.
it doesn't abort?
Yeah.
There was R Studio.
R Studio is tricky. Maybe try using base R. Have you ever tried using the base R? Yeah. That can be a problem with R Studio because sometimes like if your computer did not uninstall the previous version of R Studio is essentially like a plug-in to R. It depends on R running in the background. So R Studio can have issues of like identifying what version of R you have. And then the packages, they get installed into libraries that the direction to each of these libraries has to be defined in R. So maybe that was an issue. But like in theory, you should uninstall, when you reinstall R, you should uninstall everything that you had before. You should. Do you have a Mac or a Windows? Yeah, okay. Yeah, let me know. Let us know if you run into issues. You should. Yeah, just find the path where it is, and we can help you with that, finding that path.
The disparity of work done by the first and second.
Then we do it. No worries. Oh, is this a JCU computer or is this your personal? Okay. Because oh, okay, okay, yeah. Okay, yeah, no, that's fine. Like, because I had an issue like that because my computer is a JCU one. And then to install, they changed some security features. To install packages in R, I need to be an admin. So I need to, click to become an admin, then install the packages in the right path. It's a pain. But it's not your case, so it should be fine.
Yeah, it said something weird about this. Yeah, I was seeing this stuff and that's probably why none of this.
It wasn't undergrad.
So long as we
Like a year and a half.
Okay,
we get a draft.
Do you want a copy or something?
Okay, I'll do it. I like the process.
Yeah, in a minute. I agree.
Weird.
That's whatever I gave it back. It's on. None of my work. It seems like whenever I hand it off, like forever.
Maybe you fixed it. Maybe you had to do this. But I didn't.
I like that.
Yeah, I think they're all working. This process has so far, at least so far, it's just like that whole last step. The map.
You already have your kind of favorite. It was like something new. It's like, oh, and like what
Kevin, somebody is having the issue.
Yes. With RCPP.
But I can tell them.
They're running Mac and main.
she's on that Windows.
Oh, okay. I
It's
have
the
an
same
idea.
as Wiki.
Yeah, I just tried to give you credit.
She already.
That's the main thing. It's just that
Okay,
some.
so those ones
I think it's equal to.
Okay.
I think they fixed all the problems. When the new R came out, everyone was having this issue. Now I think they fixed it a little bit. There's like one specific version of R that is.
If you restart the session, then the other installed packages are still loaded, right? Then you have to start it.
Loading them is, they're not loading your library. Loading it and loading. Right.
Yeah, so when it says that it's restarting the R session,
The thing is like, it's like when you try to like, R to go in to do already open. It does not use those first. So otherwise it's trying to compile something that's being used and it's actually trying to interact. Define the depends on.
and the other ones you installed, they're still there, they're all loaded.
Yeah, there's the session is like closing the windows. It's like closing your application from your laptop so that you install. Yeah, we get to that in the next one. Yeah. Wait, although approach is now so trying to get the it's just using like a shiny app and you do something. You do like crazy setting.
Yeah, I've done. I've played around.
Okay, so, yeah, that one definitely was not working.
I actually am surprised that you can get
This is also what you were doing, because when I would try to run something with this, it would just give me the stop sign. And it did work, but that's one of the reasons I was installing a new version, because it kept freezing. Like the code would never finish.
That's not the thing that you're doing with this kind of lost a lot of points at once. So it's like just taking its time. Like unless it returns an error message, don't assume there's something wrong. That means it's taking its time. There's a package function for me. We needed yesterday when
Once again, it's. I mean, I
Felt
think
like
some of
something
this
was wrong, so I was doing the same thing that these two did, and theirs loaded in 2 seconds, and mine was just sitting there.
or you may just have like more stuff for them to do and put it back slower.
Yeah, let's spend the day.
I was getting a lot of red text though, so I did want to.
But sometimes red text just for your attention and you red text looks scary, but it's just telling you what the screen doesn't necessarily mean. But sometimes they give you warnings to tell you, for instance, but be careful, this version of R is a bit older than the newest one available, but that's per se not initial, that's get an error there. Yeah.
Yeah, it's okay.
Like how far away your hometown is original. But that's under Canada. Surely I'm further. But no, you're like you're farther than I am.
Oh, am I?
I guess because it goes this direction.
Yeah.
There. Like closer.
Oh, wow.
You're further. You're slow.
Yeah, because you would think
I know. It's
south, southern hemisphere.
yeah, totally tricked me. Just like it's like we're so used to like photography being like, oh yeah, like this way seems so much further than this way, but it's not the case.
I thought it would be.
I know.
Maybe it is calculated.
I think it's right. I think because if you look, it kind of looks like I guess this is just a longer distance than. It's just slightly. It's just like
I got a bit behind. As soon as we started talking about 3D stuff, I was lost trying to tinker with this.
The predictor.
Probably
Canada.
Canada.
Straight number two.
Likely.
You can start straight number three, like
So it's the east. It's a lot more if you think about it.
I'm fine if I just have it set, like, this is all gonna be out of my brain later. I'm not gonna remember half this stuff, but then if I look back at the script, I can just get that. Right.
South America.
About 90% of what we learn through our normal receptors gets swept out of our brains within the course of 6 hours. 6 hours from now, it'll be like you never did that.
Belo Horizonte. You have to say the G.
All right, so they're all loaded successfully. There should not be any Ggplot problems.
Belo. It's more than that.
Yeah, that was beautiful.
Oh,
Because
that's
it's
fine.
very easy.
That's one was used to make natural methods. And then put it like that.
Yeah, you can go really far.
Quito, no Ecuador. Quito is 14. I made it.
Like the first building is responsible for pretty good big old architecture.
Yeah, Quito. It's a colonial.
It's very different from. Yeah, it's more
It's
Spanish
Highlands.
style. Makes sense, but in Brazil, obviously it's Portuguese.
Yeah, we have like the story, like CBD. It's a very, very true. Because there was Spanish when there. Quito was a very important city for the Incas, and they established.
Art frustrates me.
Built
Art
on
is
top.
very sentimental.
I know, it's like a very high maintenance. It's
No,
like
there is
friends
not,
that
there
you,
is nothing.
like, are forced to hang out with, but you don't actually like.
Remains, yeah.
That's
And then, but then you can, like, any other construction that is done around that area, you can find like an.
Like running people around for lack of better options.
Yeah, treasure, because they put the machines down.
No, this is why ours acting up.
Wow, that's fascinating. You can be in the middle of the sea, taking photos and finding.
Yeah.
Yeah, no, so they.
Yeah,
Is
our
this
stereo
like-
batteries
Sorry,
help
That's the room we were before.
It's the room that we were
Yeah.
before. I can turn it on.
See that no one's there in the room.
Oh, it does the green screen every now and then.
That's so fun.
It goes through.
If I turn it off, it will not turn off everything.
Oh, okay, yeah, let's just leave it. It's just in case.
Just in case.
Not our problem.
Feeling it there or no, but it's taking its time.
You have it.
Oh, it's really nice. It's interesting, you know. Please tell me how to replace it.
Now it just sounds like I'm groveling.
Every hour, like, okay, here's the time where we do a little later.
I mean, she gave us this one.
Hello.
That's why it's real.
Okay. Are we back? Back.
Oh, and then it doesn't stop to do it. You can quit.
All good there, Lorenzo? Are we almost?
You can go on without me. I'm just
Are you
having a
sure?
problem with the SF package.
Yeah, we're having a problem with units and ours. Yeah, I don't want to install ours in case like the war.
Oh, the problem is with our CPP, the whole thing.
What is the RC?
Yeah, just install it. Because this is not a Mac. The problem with RCPP is with Max. Just install it. And do you know if you have any C++ compilers in your computer?
I don't even know what that is.
So it's probably gonna be fine. Just install RCPP and it should be fine. Aloha. Cool. So you guys are probably now tired of all this talking and never-ending basic stuff. Let's do some exciting things. But I hope you've understood the basics of plotting maps in R. We're still gonna do a lot of basic stuff, but now we're start to progress into the actual, let's try to make our plots look nice, which is the goal, right? All right, so now you can all open your script number 3, in which we're gonna deal with many of the things that you've asked. I mean, 2 questions so far. So these 2 questions are gonna be answered in this script, this present script. And for this script, we're gonna load many libraries at the beginning. Ggplot2, you know what it is. SF, now you know what it is. R natural earth, you know what it is. R natural earth data, it's a new one for you, but essentially what it is not only it gives you a polygon of the world map, or many polygons, right? In each individual country is a polygon, but it also gives you some data associated with that world map. Let's say longevity per country, things like that. You can find in our natural earth data. And you have GG spatial, which gives you some nice plotting features in Ggplot. So it's an add-in to the Ggplot world, but specifically for maps. And we're gonna see some brilliant things it does later on. And tidyverse, which if you're not familiar with it, it's a great package for data manipulation and exploration, whatever. This is the package that does the thing that I was explaining, the piping thing earlier. Well, yeah, before I progress, I think I forgot to maybe mention at the beginning that I assume that people are familiar, or at least a little bit familiar with the Ggplot plotting functionalities. But if you are not, please feel free to interrupt me, because sometimes I just go through the code assuming that you know roughly what it's doing. But if you don't, that's okay. I will explain and just interrupt me, okay? Please do that. I don't want anyone to feel lost and feel like they should know something that they don't. Okay. And to start with, because we're going to be using Ggplot for most of this script, you can, at the beginning of your script, already set a predefined theme at which all of your plots are going to be plotted using that basic theme. One good theme to use for maps is this theme BW, or theme black and white. It is the normal black and white grid, it's a traditional plot, but I like it and it's good for maps. So let's just use this function theme set and set the theme BW for all our subsequent plots from now on, okay? And again, let's turn off that function that uses spherical geometries, because we don't want to have trouble plotting axes and things like that because of geometry problems. Cool. Let's start by always first thing to do when you're wanting to plot a map is to load the polygons or whatever you're gonna plot in your map. So to essentially load your map. As you can see, the beauty of R is that it has lots of preloaded polygons that you can use that probably for most people, that's all you need to plot your maps. In some cases, as we're gonna see later on, this world or our natural Earth data is not gonna be enough because it won't give you the resolution you need. But that's a subject for later. Cool, let's load it. And now finally, as I said, let's have a look at what world is, the world object. So we just loaded, again, using the function NE countries. And what is the class of this world object? That's what I'm doing there. I'm just asking, what's the class of that world object? And then R tells me, oh, this world object is an SF. Oh, brilliant, because I told it to return a class SF. So it is doing what it's meant to do. But more important than that, it also tells you that this world is a data frame. That's curious. I thought it was just an SF. Let's have a look at what this SF is, finally. If you just call world without anything, you're gonna see what is behind the world. I think that's what you were asking earlier. So let's have a look at what an SF object looks like. It starts with, you can go up until you get to the point where we called it. Every SF object comes with this description of the data, first of all. What is world? World is a simple feature, SF, stands for simple feature, collection with 241 features and 63 fields. This is super cool because the SF allows you to add not only the geometries, which are the features as it is calling here, but also it's giving you 63 fields of data. So that's extra data that our natural Earth package gives you. Just like when you load the world, it doesn't only gives you the polygons, it gives you a lot of data associated with each of these polygons. And soon we're gonna understand how to explore this a little bit. And it tells me, oh, what type of geometry are we talking about? We're talking about a multi-polygon geometry. This is a little bit of, yeah, all right, let me explain this. Essentially, this SF object is composed of many polygons. Each polygon is a country or a geometric feature on a map. That's why this geometry type is called multi-polygon. But you can have maps that are essentially just points or lines. So you can have, for example, a geometry type that is composed of points. Remember in the first script when we plotted the points on top of the maps, we did it perhaps the most crude way of adding points to a map, because you can add points to an SF object, giving it coordinates in the whatever projection you're looking at. Cool. And also it gives you dimension, X and Y. Remember, you've asked, what is the default projection? Now it's telling you, yeah, this projection is in X and Y coordinates. Lat and longitude correspond exactly to X and Y. And it even gives you what are your X mean, or X-axis goes from minus 180 to plus 180. Brilliant. There you go. And the Y goes from minus 89.999 to plus 83.533, 0.5, blah, blah, blah. Essentially, it is telling you how big the world is in this X and Y coordinates. Okay, and then we get to this CRS. CRS is a slightly more complex concept, but CRS stands for Coordinate Reference System. What this line of code is telling you, or this line of data is telling you, the combination between these things is telling you what CRS we're using. What coordinate reference system are we using? And the first thing that it shows is this proj equals long lat. What that means, again, is that the projection that we're using corresponds to X and Y coordinates on a Cartesian plane. And we're gonna see later on how we can change this projection. You might have heard, for example, about the Mercator projection, which is the most commonly used map projection in the world. To generate a Mercator map, we need to change the CRS. We need to change the coordinate reference system of the SF object. Brilliant, cool. And then it gives you the first 10 features of this SF object. So let's look, for example, at some of these features that the SF gives us. All you need to do is the same as if you had a data set. When you have a data set and you call head that data set, you see the first 5 or 6 rows and 5 or 6 columns, right? And that's what it's doing. It's showing just the 10 first rows of what we have here. But then we have many column names. We have this column name scale rank, which I have no idea what it is. It has a feature class, which I have no idea what it is, but it has some other interesting things. For example, if we go down, it says, if, for example, a geometry is a country or a sovereign country or a dependency. So this is what the type column is, but it also tells you the name of the countries. Remember, each polygon has it represents a country. And because that object world is both an SF and a data frame, the data frame tells you what country is this polygon corresponding to. Because if you look at the same line, so let's look at row number 0, and let's go all the way to the end of this world object. There is something called geometry there. And geometry is exactly what the SF part of this whole object is. This geometry, if we call it, so you can visualize an SF object the same way as you visualize any data frame. So you can call, for example, world, I want to check geometry number 1. What is the geometry number 1? It's not, it doesn't give me the whole thing because it's a bunch of numbers here. What this bunch of numbers is, pay attention because this is the most important thing for you to understand what a map is. These are X and Y coordinates of this first country. So I called the first line, which corresponds to the country named Aruba. So Aruba has this polygon that has a bunch of X and Y coordinates, one in front of the other is another X and Y coordinates, X and Y coordinates. These are the points that define a polygon. It's essentially tracing the lines between points. But here we have many lines connecting dots. These lines, considering their X and Y coordinates, generate the shape of a country. That's what it is. As easy as that. So now I hope you understood why I wanted to go through those basic steps beforehand, because it makes it so much easier to understand what this is.
So the only feature that makes a data frame an SF is that column geometry.
It's not a data frame, so it is an SF. The data frame, so world is both an SF and a data frame, but it could be only an SF if you didn't have any data associated with it.
It would be only the geometry.
Only the geometry.
Right. Okay.
Yeah, makes sense?
Yeah.
So For example, we can also look at the data. We can call, instead of calling geometry, we can subset from world, we can subset, let's say name, Aruba. This is very, very useful later on, because then we can associate, we can use all the functionalities of, for example, Ggplot and Tidyverse. You can filter data in your maps. Like I told you earlier, you can filter Australia. I just want to plot a map of Australia. Filter Australia based on the name. As easy as that. So this is super cool. This is the basic structure of an SF object. And if you are familiar with what a data frame is, you are familiar with what an SF is. That's as much as you need to know. Okay, let's get into plotting. Enough of talking about all of this background stuff. Let's do a very basic world map. All you need to do is to call the Ggplot. What kind of data are we inputting into Ggplot? World, which is a bunch of polygons representing a bunch of countries. And that is a world map. Okay, now there was a question earlier. What is Chord SF and Geom SF doing? Very important and relevant question. So I think the person that asked that was on Zoom. I hope that person is still there. Haven't fallen asleep yet. So Geom SF, if you are familiar with Ggplot, remember to plot a point in Ggplot, what do? You call Geom point. To plot a polygon, a geometry in Ggplot, you call Geom SF. As easy as that. It's this function, Geom SF, is a Ggplot function that plots polygons or geometries given a combination of coordinate systems that we have. And Chord SF is the argument or the function that deals with the axis. So you can define a bunch of features here in the Chord SF that will be related to your axis. So for example, if you want to establish the limit of your plots, you use xlim, ylim, right? Those things you can use inside Chord SF, xlim and ylim. If you want to limit in x and y, if you want to zoom in any of these countries in the map, you define x and y. Where do I want to zoom in the map? That's what you define inside Chord SF. And the only thing I'm doing inside Chord SF is this expand, which I'm making it equals to false, because as a default, it expands a little bit the plotting. We can just turn it into true and see what it does. It just gives you a buffer zone around the map. Did you notice that it changed a little bit the limits of the map? Some people like that because essentially what this expand does is it avoids the map to overlap with the axis, but we don't need that now. And I most of the times just put expand equals false, because then you know exactly, when you do expand equals true, you kind of lose the sense of x and y coordinates because it changes it. It expands it a little bit. So I do expand equals false. And then we have a map with our axis and lovely. Cool. And then I've explained a little bit there. So this is what we call an equirectangular projection, Ricardo, with longitude and latitude x and y values on a grid. So I've already now explained it in many ways possible. I've just given you the name of this coordinate, of this projection, sorry, of this projection. It's called a equirectangular projection. This is the default projection for maps which is the base R way of plotting maps. And this is the default for our natural Earth as well, and ggplot. Cool. Now let's start changing our map. Let's try to, the whole thing, the whole reason why we're here is to make nice looking plots of maps. So things that we can change, for example, in this plot is we can add, oh, this happens a lot. If you came across this error, don't panic. It's organic. It's just a problem that ggplot has with RStudio, I think, that when you define, it's hard to explain, but when you plot a first figure and then you try to plot another one using that same plotting area, then it doesn't really work sometimes because the plotting goes beyond what the plotting of RStudio is, and then it returns an error. All you need to do is to clean your plotting device just by using this dev.auth function. Just cleans your plotting, and then you can plot that again. So hopefully it won't return the same error.
So that off it's like a RM for plotting, like a remove for plotting.
Yeah, kind of remove. Yeah, you're removing the plot. You're cleaning the plot. You can, yeah, you can kind of say that. RM, you're removing stuff from your environment up there, all the things that are saved in your environment. Yeah, sort of. Okay, cool. Now, all we've done is we added axis labels. So we have longitude, latitude, and we gave it a title for our map. And if you check what I'm doing in this GG title line here, I'm using the data within the world SF object. Because remember, world name, if we call this, it's going to give you the names of all the countries, the 241 countries that we have in our data. And if you check world again, remember that at the top, it's showing you, oh, we have 241 features. Coincidentally, we have 241 names. Each feature within that world has a name, that world object. So if we call the length of unique names, it's going to get us 241. And then I'm using that to plot on the title. Oh, this world map is showing 241 countries. So what I'm doing here is just showing you a way of already using the data that's within the world SF object to plot. So you're not manually typing, oh, this has 241 countries, because then when you load a different SF, it might have 240, and then you're going to be wrong. So instead of manually typing, you use, oh, how many countries are there in this object? That makes sense. Cool. And now getting into some other stuff. Remember I told you about like changing colors and things? If every country is a polygon, we can change the color of the polygons. So inside the geom SF, you can change it to the fill argument to light green. And you generate this horrendous map, right? But it's okay if you like it. Personal taste is something that should never discuss and get too deep into that. But that's okay. I don't like it personally. So I can change that color instead for a tone of gray. And I can make, remember, this can be kind of tricky because the fill is what defines the color within the polygon. So you're filling the polygon with that color, whereas the color is defining the borders. So if I make the borders transparent, there you go. You can still kind of see them, but they are very thin lines. Now, so this is slightly better. And another thing that you can do is instead of, for example, you can make the lines, instead of making the lines transparent, you can make the lines of the borders the same color as the polygon, then you're gonna make them disappear completely. That's what I did here. So both fill and color have the same color, and you still can see it, but that's, yeah, it kind of disappears. Right. Now let's make it a little bit more exciting. Remember that SF object, or our world object, has some data with it. So it's as easy as, if you want to plot some data using that data, you can first generate your map. So I'm just going to run these 3 lines of code here. And what I did is I said, instead of using the fill as a specific color, I'm giving it an aesthetics. So this AES stands for aesthetics. That what I want Ggplot to do is to fill the polygons according to data. And it does that automatically for you, giving you this default blue gradient of colors. If I just define, I want the estimated population size, which is inside the word object. So again, if you call world pop est, let's find it, pop est, pop ear, pop est. What is it? A bunch of numbers corresponding to the population size of each polygon. Brilliant. But then, if I don't like that blue scheme, I can use the Viridis, which is a colorblind friendly set of color palettes to represent the estimated population size. And that's, I'm not entirely sure what year does that correspond to, but that doesn't matter for us now. Just showing you how you could plot data as easy as that in Ggplot using maps. And another thing that I did there, if you look inside the scale field Viridis, I called an option called plasma. That's defining what palette I'm using. There's multiple palettes. There's magma, there's Viridis, there's plasma, and others. And I use that argument trans, which is, it stands for transform. How do I want to transform the gradient of colors that I'm representing? I want a square root transformation because that increases the differences between max and minimum values. I want the maximum values to stand out. I want China to be bright yellow and India to be bright yellow. And that's fair. You're not modifying your data. You're just modifying how you're representing your data. So you could change that. For example, there's multiple ways of transforming the gradient of colors. And you can see this in effect here. If you just change it to log 10, you're going to see that it changes completely how you visualize your map. But then, well, China and India are not really standing out that much, are they? So a square root transformation gives you what you want. This is what you want on your map. You want to convey a message. You want to show something. What do you want to show? And what's the most effective way of showing it? You use a square root transformation. Or we can use no transformation just to show you how it looks like without any transformation. And they do stand out, but the other countries also get, too blue, too like, because the differences are so big that like you lose those differences between the smaller population sizes. So a square root transformation gives you a good, let's say, good balance here. And this is not cheating. We're not modifying our data. We're just modifying how we're showing it. If you say on your figure description, this is showing population size using a square root transformation for the scale of colors, you're being completely transparent and honest with your reader. So I'm not modifying the data. I'm just modifying how I'm showing you. to convey the message I want to convey. Okay, cool. Now we start playing a little bit with projections. So let's see how can we change the projections of a map. So if you are an alien that's getting to the Earth from the north, there is a projection for that. You just, inside chord SF, you change the CRS argument. And in that case, I'm giving it a specific kind of coordinate or a projection that I explained down there. It's called the European-centric Lambert azimuthal equal area projection. Does that matter? Nah. Just wanted to show you there are many different projections of the world map, depending on your goal. So this is one way of seeing the world map. It has its own problems, just like every projection. Look at Australia, how giant that is and crazy, completely distorted. But Europe is perfect. That's why this projection is good for Europe, for example, for a map of Europe. It's almost nothing is perfect. Sorry, I saw your look when I said perfect. You were like, you're right, it's not perfect. Cool. Now stop playing with this and let's get to the, for example, the Mercator. Oh, and remember, what is CRS? CRS, coordinate reference system. All you're doing is within the SF object, you're changing the coordinate reference system. Now, if you want to change that for the Mercator projection, which is the most widely used projection in the world, all you need to do is within the chord SF, you change the CRS and you just give it the argument plus proj equals merc, because then you're just changing the projection. You're not changing all those other things that got defined in the CRS. And then voila, you have a Mercator map. How beautiful that is. No. Problem with Mercator is it was a very good map for early navigators because it depicts always north is always north, south is always south, because it's essentially get the globe, draw a cylinder around it, cut the world map. What it does by default then, it distorts completely things that are far from the equator. So things that are close to the equator, the area, it's relatively faithful to what it is. As you move further from the equator, those distances get blown up. And this is exactly what's happening there. It inflates the distance so much as you move towards the Antarctic that even Ggplot goes completely crazy with that projection, because it's using a mathematical formula to calculate how do I transform these things? And then it just, I don't know. So for example, if you really want to keep using a Mercator projection, how about remove Antarctica or Antarctica? You can filter out Antarctica because remember again, world is a data frame. So if you use the function filter and if you're filtering the code, this ISO A3 just gives you codes for the countries. And I know that the code for Antarctica is ATA. The code for Australia is AUS. So just another code. But anyway, what I'm doing there, if you guys are familiar with this, I'm telling it from that data frame, world, give me everything that's not ATA in this column. So I'm filtering ATA out, Antarctica. And when we plot that using the Mercator projection, off we go. Less horrible, still horrible, still horrendous. Because look at the size of Greenland comparing to Africa. And that's the main criticism of the Mercator projection. If you look at Europe, Europe's also kind of giant. Europe it's actually tiny in terms of area. And when you compare like Europe to Africa again, Africa gets tiny. Africa is huge in area. And again, the problem remains, but if you want to use it, know the issues that you're dealing with. Right, but we have less distorted options. One of them is called the Robinson projection, which was specifically created to find this good compromise between the problem of showing the whole globe as, you know, a two-dimensional Cartesian coordinate, because it compromises the problems with distortions in area and distortions in distance. So this is probably one of the best resolutions they got in terms of like less distortions in all the parameters that could be distorted from a projection. And then if you run that, again, all you need to change is the coordinate reference system to plus proj Robin, and then that gives you a Robinson projection. I do like that projection a lot, actually. And by the way, if you're looking at that projection, if you're like, oh, this is perhaps the world map that I'm most familiar with, it's because, for example, National Geographic uses this projection in most maps they plot. So it's a good projection to show the whole world. And then there's another projection which is called the Moe-wide projection. And I hope that at this point you're understanding that the difference between projections is how much do you gain in certain distortions, how much do you lose? Because again, you have distortions in distances, area, and shapes. So these three things, what's the trade-off between them? How can we fine-tune them all? It's always gonna have problems. There's never gonna be a perfect projection. But how do we fine-tune them? And that's up to you. What do you want to represent with your map? In this case, this projection, it is a pretty good projection for maps that are depicting global distributions, because it trades, as I'm saying here, the accuracy of angle and shape for accuracy in proportion in area. So if you want to show the proportion of areas between countries to be more precise to what it actually is, you use a Moe-wide projection, and this is how it looks like. And then you look at it and you're like, oh, wow, it looks like it really flattens the polar sides of the Earth. What you're seeing is a distortion. This is how it distorts the data. To the trade-off is we get a better proportion of areas between places. This is what the Moe-wide projection does. Okay, cool. And just a quick pause in Ggplot here, because you can also do that using base R plotting. You can change the projections. Again, you load the maps, and then using maps, you can plot the Mercator. Again, maps is apparently a little bit more clever than Ggplot in the sense that they just cut Antarctica, because Antarctica is certainly not, doesn't go all the way. And it gives you a warning. Projection failed for some data. Why? Because it's too distorted. Where Ggplot plots it for you, this one gives you a warning and says, I'm actually not very comfortable with plotting this very distorted map. And you can plot, for example, this map, which it's very interesting, like how us primates are. When you look at this map, you're like, oh my God, this is horrible. This is very distorted. This map is an equal area projection, or a Peters map, that shows the area. So this is fine-tuning area more than anything. Area of the continents is pretty faithful to what it actually is, whereas the other things I don't care. I don't care about distances, I don't care about shapes. It looks very distorted, but this is the actual size of Africa compared to Europe. Look at the difference between this and the Mercator projection. This is crazy. And I love this map because it really breaks you into like, I'm so used to that Mercator projection that this looks horrible, but this is the actual reality of the world in terms of area. I like this map so much that I have it in my toilet, right next to it. Anyway, not exactly this one, but a more pretty one. I'm just showing the really default way of plotting a Peters projection. Excellent. Now let's start making our maps pretty. That's why we're here for. So let's say we want to now finally zoom in a specific area of our map. And for the purpose of the exercises here today, let's stick with the X and Y coordinates, the default coordinates that it gives us, the flat map, right? So let's not change the projection for now. So let's plot a map of Europe, for example. All you need to do is to define a bounding box that gives you limits in the x-axis and limits in the y-axis. Those limits are the same. You're just creating a box where Europe is. Those are longitude and latitude points. So longitude, latitude, longitude, latitude. As you can see in the axis, it goes from 30 to 65, which is what we defined here. It goes from minus 14, remember the minus, tricky here, to plus 30. There you go. Cool. What else can we add to this map now that we are finally talking about making maps look pretty?
Pizza restaurant.
An Italian restaurant. So, Lorenzo, you are responsible for plotting a pizza shape right where Italy is in this map, while we move on with the rest of the workshop, where your hometown is, and then we can show it to everyone. Right, but what, other than the pizza in Italy, what else can we add to this map? What is missing here to be a quality? Sorry?
Like a compass pointing a north arrow.
Nice, great point. We need to know where north is. I don't know where north is. I don't know if Norway is to the north of Italy. But there is a way of knowing. And it's very easy to do that using the GG spatial package that we loaded earlier. So if you run this next line of code, not only it is giving us a north arrow, but it's also giving us a scale. We need a scale bar. Our maps are nothing if we don't have a scale of distances. But then you might have realized, oh, red letters, bad thing. Yes, red letters, usually you should pay attention to them most often. What are these red letters telling you? Scale on map varies by more than 10%. Scale bar might be inaccurate. Why? I ask you.
If the distances are not always the same, distances between two points, not accurate.
But why?
Because of the projection.
Yes. Point for you.
Is correct.
Exactly. You are plotting distances on this map that is distorted. So it will most often give you this problem. So if it differs more than 10% from the actual distances that we know, it will give you a warning. Look, pay attention. This scale bar might look pretty, but it might be 10% distorted from the actual distances. Do I care about that? I don't know. What's my goal with my map? If 10% distortion in distances is something that is I'm worried about, I need to use a different projection here. Does that make sense? Right. What else can we do to make our? Oh yeah, I forgot.
Can I have moved the north arrow, for example, to the left of?
Yes. Good point. I forgot to. I just ran the code and forgot to explain. So the functions adding these things is annotation scale, which gives you the scale bar. And location is exactly what you're asking. You can either define location by BL, which is bottom left, or top left, TEL, or top right, bottom right, or you can even specify coordinates or proportion on that map, on the X and Y coordinate. So I recommend you to call for help in the annotation scale. Ask R, what does annotation scale does, and how can I change the location of that arrow? Oh, in this case, I'm talking about the scale bar, but it's the same thing about the arrow. Is if you look at annotation north arrow, the location is, I'm also plotting it in the bottom left. And then I'm defining other features of it, showing like, oh, which north? Yeah, true. It's showing me the N on top of the arrow. Pad X is like how much, pad X and pad Y is like how much do I want to move it slightly on the X and Y coordinates, because I don't want it to be on top of the scale bar. If you just run location equals bottom left, it will plot the arrow on top of the scale bar. And then style. Style is if you ask R, oh, annotation north arrow, what styles do we have in option? It will tell you. Style. If you come here, see north arrow orienting for options. Okay, then you click north arrow orienting. And then you have so many north arrow orienting, north arrow fancy orienting, blah, blah, blah. All of these are options that you can change to if you want to make your fancy north arrow look different. Okay, cool. Is everyone on board? So these two functions are handy and easy functions to add these nice features to our map. A north arrow and a scale bar. And they come from the GG spatial package. Right, let's add ocean names, and I got the same error again. So what do? I just clean my plotting area, and then I can run this again. I'm using the annotate function in Ggplot to add text, essentially. And I'm giving X and Y coordinates, as you can see inside the annotate functions here, X and Y. Where do I want my Mediterranean Sea to be? I want it to be, oops, here. So X and Y. And again, X and Y for annotate. And then we're also giving labels to X and Y by XLab, YLab. And remember, chord SF is just trimming the world map in the coordinates that we want. Cool. Now, let's get to the final map. What else would you do with this map? I, as a marine biologist, like to see the ocean blue. So let's paint the ocean blue. And stick with all the features. And now you're seeing, for example, how Ggplot works, because remember I said it's like additional, like you just can keep adding features as you go. And one more clever way of doing this would be to be saving each plot as an object, and then I just add to that object later on something else that I want to add. You could do that as well. So for example, okay, now we have our map of Europe here with the colors that we want, looking nice. So we can save that as a, let's say, plot 1 is going to be equals this. And then if you call plot 1, it's probably going to plot you if our studio stop. Oh, did I create that? Oh, no, it was right. It was trying to correct me, and then it
plots a map. Does that make sense? Cool. So all the things I modified here to make the ocean blue and blah, blah, blah are actually inside the themes, because this bit here in the background, it's the panel background. So we need to adjust. So this is a Ggplot feature. This is not a mapping feature. If you have any sort of graph and you wanted to modify the background of that plot in Ggplot, if you wanted to change the color, you would do the same thing. And this panel grid major, it's modifying the lines here. As you can see, I made it look fancy. I turned it into a gray, and I made it dashed, and I changed the size of it. So it looks okay. I like this map. If what you want is a map of Italy, right? Do you have a pizza for us? Nice. So, are you happy with this map? Anything else you'd like to add? We can add points, we can add lines, just define whatever you want. Pizzas, whatever. And to save, you can just use GGSave. GGSave saves whatever is in your plotting area. And this is going to be the first instance in which you need to change the directory. So what I'm giving here is the path to where my maps folder is saved in my computer. So maps is in my desktop. If you have a Mac and if you save the maps folder in your desktop, you don't need to change anything. If you don't have a Mac, you have to figure out how to find the path to your folders, which is something that I assume you probably know already. Yeah?
Sometimes when I want to save a plot, like for example, some journals tell you you need 300 dpi, that's size, and so I input. But then when I save it as an image, it just distorts the graph so much.
Yeah.
And so what I do, I just click export and I just have a look at it and sometimes.
Yes. I get what you're saying, and that's very frustrating indeed, because setting the right proportions in the figure can be very tricky. So for example, in GGSave and in any other saving devices or functions in R, you can define height and width. That's going to define the resolution of your. Okay, let's go back one step. I always save my figures as a PDF. Reason why? PDFs are vectorized. They never lose resolution. Do you know what vectorized is? Every element in your plot is, you can modify it if you open, for example, in Illustrator. Always vectorized. Whereas if you save a PNG or a TIFF, that is a flat image. You can't do anything with it. It's a flat image that you define the resolution. So in this case, I'm saving a PDF. And then what you can do is you can define height and width. So say height, and this is in centimeters, I think. Let's put 8. Width equals 8. So I want a square plot. Let's see how it looks. Returns you the problem. Let's see if this looks okay. Yeah, it looks all right. But probably what's happening to you, Ricardo, is that, let's say you are saving it in height or width 2. Let's see what it does. Look.
That's exactly what happened to me.
There you go. So you need to define the size of it. You need to define the proportions. And unfortunately, there's no silver bullet here other than trial and error. Unless someone knows how to do it, Kevin and Lorenzo. I've always struggled with that as well. So don't worry about it. It's a matter of, in my case, it's trial and error. And then when I find the right proportions, I save it and then never touch it again. But the default of GG save usually gives you a good proportion. It tells you, because if you don't define height and width, it will tell you, oh, saving maps on, there you go, 8.96 against 5.79 inches image. So that's the default of GG save.
That's the size of your plotting window in R.
Yeah.
So if you set it up like that, it'll always not specify width and height. It plots it at whatever size that window.
Great.
And
yeah. So that's probably what's happening to you. So you're just using the default. It saves whatever resolution you have on your plotting area in R. So now, yeah. So it's exactly the same as this. Cool. Right. Does that make sense?
Yes.
Hope it helps. Now, you might be asking yourselves, how can I change the projection? If we talked a lot about projections, so we want to plot that same map of Europe, but changing the projection. Now things get a little bit trickier, because if you once you change the projection, you cannot use the same idea of plotting X and Y coordinates. Then your X and Y disappear. You need to then, if you want to plot a point, you need to transform that point into that projection. Luckily, SF does all of that for us. So I'll give you an example. The first thing, if we want to plot a map of Europe with a different projection, we can, yeah. Yeah, yeah.
In the map, when you are adding the ocean names, you just adding it words, not the text. That you just specify the X and the Y in the accent.
I'm not sure if I understood the question. Sorry. Can I do?
I guess that if the X and the Y in the plot that you're taking the name of the ocean means something in the map, or the SF already has the word?
Oh, no. That's a good question, because that's exactly what I'm trying to explain here. Once you change the projection, you cannot annotate the ocean names in that same place, because that's not going to correspond to X and Y anymore. So the reason why I'm sticking with the default projection in this map, for example, it's because if you look at the grid follows exactly what X and Y are. So I know where X and Y are. So I can say, I want the Atlantic Ocean name to be in X equals roughly 10, minus 10. There you go. And I want it to be a Y equals 46, let's say 45 something. Then you can do this. And that's what we're doing right here. So yeah, Atlantic Ocean, X minus 10, Y 46. Problem is, when you change the projection, that does not work. That's why you have to think about, do I need a projection? If yes, you need to know how to transform your points, or you need to know how to find the right coordinates in your new projection. That's what I'm going to do now. Does that answer the question?
Answer another question. I think she was asking how you define what text you want to be plotted, as in she wasn't unclear of the label argument. Like, how do you know that you are writing Mediterranean Sea? Is because you provided that as an argument to the label.
Yes.
I wrote that in the room.
Oh, yeah. Oh, right, the label. So label equals Atlantic Ocean. You can write my ocean if you want. Then it's going to plot your ocean.
And then you want it.
And if you write that, then it becomes yours.
It becomes yours, yeah. If you plot pizza on top of Italy, you're gonna find pizza there. Right. So, okay, first thing you need to do when you are gonna change the projection is, remember before what we did, we knew X and Y, so we just zoomed in the world to get to Europe. But again, like I was only able to zoom in because I know that X and Y correspond to latitude and longitude, or longitude and latitude. But once you change the projection, I don't know where Europe is. I can't just go to the Cartesian plane and say, what are X and Y? So the first thing you need to do is to use this function stCrop. I want to crop from the world map. So you're giving world to stCrop. And I'm cropping it right where Europe is. That's the first thing I'm doing. I'm just cropping that map. Poof, and creating a new object. Let's have a look at Europe, what Europe is. Yeah, it gives you another set of warnings. Again, just telling you that things are distorted, okay? But now let's look at Europe. Oh, first of all, what's the class of Europe? It's still an SF and it's still a data frame. What stCrop did is essentially it went to the world object and it cropped everything that was inside these X and Y coordinates that I gave it, including the data element. So anything that fits inside that, it's going to be filtered. So it's going to be cropped. Now that we cropped it, and the reason why we're doing this is because we're not going to be able to zoom in once we lose the X and Y coordinates. And that's what we're doing in the next line. So the function stTransform, you can transform the coordinate reference system of Europe to a Robinson projection. So I'm just changing here for a projection equals Robin. So our Europe Robinson now is this. But look what's interesting here. We changed the projection. Let's look at, for example, Europe geometry, first element of geometry in Europe. X and Y makes sense. Europe is still within X and Y coordinates, or that equi blah, blah, blah projection. But once we transform it, so if we call Europe Robinson geometry, the first geometry, look at those numbers. They're not X and Y anymore. I'm completely lost. I don't know how to plot a point in Italy with a pizza now if I plot a map with this, unless I plot my point in the traditional coordinate system, transform that point into a Robinson projection, and plot that point in Italy. And we are going to do that. So let's just look at how Europe looks like using the Robinson projection. There you go. Now you know why we lose our X and Y coordinates. Look at this map. It's funny. It doesn't look flat anymore. It looks like it has a curvature, which makes sense. The world is not flat. It has a curve that corresponds to how the Robinson projection projects things on a two-dimensional space. But now your X and Y coordinates are gone. You can try to plot a point there. It's hard. You won't know exactly where those points are. So you now need to plot a point that corresponds to this new coordinate system. This is a new coordinate reference system. How do we do this?
I have a question.
Yeah, go ahead.
Same result by plotting the world and then changing the coordinate system with coordinate and then cropping them up. Do you get the same thing?
No, because the crop, you're giving X and Y values. If you transform it before, X and Y are gone.
Right.
You are gonna have to figure out what does this X correspond to in the new projection. That's why I cropped it before, because I knew the bounding box that I wanted, cropped before, then transformed. Right, cool. I hope this all makes sense. Now we have a challenge for you. I want you, now don't worry about projections. I want you guys to plot using the normal, the default projection, but I want you to plot a nice map of your region of choice. It can be the continent where you come from. It can be your country that you come from. And yeah, plot using your preferred map features. If you want to change the color of the ocean, if you want to change the color, things that you learned so far, do a nice plot for me, please. In the meantime, I'll be changing the code here to show how you plot, how you transform a point now into the new coordinate system. Cool.
Do you have the coordinate series? No, it's the rating.
I just wanted a point that represent where's your hometown?
Milan.
So give me the coordinates of Milan.
It's next to the ice cream shop.
Next to what?
45.464 north.
35 point?
45.
45. 45 point?
464.
464. Okay, and
9.19 east.
No, wait, are you giving me?
Milan?
Yeah.
It's a bit harsh.
And 9. It can't be 45.
Yeah.
Oh, 45 on latitude. Okay. First you give me X. That's okay.
9.96.
And what's the other one?
45.45 something.
No, the longitude. Is it 11 point something?
9.96.
9.96.
Yeah.
Oh, that's because Milan's here. Yeah. 9.9.
I found the workaround for the last script, by the way.
You did?
Yeah.
What script? Oh, yeah. I also know a workaround for that, but yeah, let me know. So, okay, now we have a point. What we do is we transform point into the same projection. So, point rotates. Oh, no, this is going to be S T S. What's the function? Yep. S T S S F S. Let me come to STSSF. Yeah.
What does this stand for?
ST. I'm not entirely sure. Simple. I'm not sure. So ST is that. Yeah. Okay.
I'll work on my 6-7. Got it.
right. Hello. 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 So, have we got beautiful maps? Very beautiful.
I'm not in a verb. I'm trying to find Ecuador.
That's okay. Nice. Get in there. Cool. Wow. You've been plotting points. Very good. Well done. Nice. Very nice. Yeah. Oh, this is cool. We're going to come back to it in a minute. Are you trying to plot an island? Nice. What island is that? Mauritius. Cool. That's one of the things that we're going to deal in a minute. Cool. Nice. Very specific. Oh, was it just because I looked at it? I'm sorry. Cool. We have some Australians here. Nice. Okay. Italy. Oh, South America. Very nice. Very nice. Well done, everyone. Cool.
Now my beautiful map is gone.
That's okay. You can do it again because you're free. You're independent. You are great. You're going to do it. You know how to do it now. So no reason for desperation. Cool. So now the challenge is I was going to suggest that you guys plot. So far, you probably realized that we've been looking at, maps on a more global scale. So, continents and all of that. But what if you're working on a more local scale? So I'd like you to try and plot, for example, a map of Lizard Island. Or in your case, you can try to plot Mauritius. But for this exercise, try to plot Lizard Island and see what happens. Again, Lizard Island, you can find the coordinates on Google Maps. Or in your case, Mauritius works the same way. I'll explain why. Maybe you're a little disappointed with your map. It was not a very good resolution. That's okay. I will explain the reason why in a minute. Don't be too disappointed at me now thinking, oh, you're such a fraud. Not yet. We'll get there. Is this your pizza place?
Yeah.
Does that correspond roughly to where it is?
Yeah.
Yeah, okay. Yeah, I might kind of go a little faster in this because we're not running out of time, but the most important bits are coming. So if anyone has already tried plotting Lizard Island.
I almost got it, I think.
Almost. Some people almost got it. There you go. Tried Orpheus, only getting water. What's happening? What's happening? What's going on? Huh? Maybe. So if you tried to plot Lizard Island, more likely you won't be able to, or Orpheus, you only see water. Reason for that being, remember our world object, it's on a medium resolution. And we've done this for a reason. We don't want to deal with maps that have very high resolution because it becomes really heavy to work with them. So this map, this world map, doesn't give you every little tiny island. For example, Lizard doesn't even appear. But in the case of Mauritius that she tried to plot, it is there. There is a polygon representing Mauritius, but the polygon doesn't have the coastline very nicely drawn because it's essentially the resolution that we're using on that world map. And this can be a problem if you're working on that scale. You need to find shape files that correspond to that coastline. Unfortunately, I don't have the high resolution shape file for Mauritius, but I'm pretty sure you can find it online. But in the case of Lizard Island, we can download it from the AIMS website. The Australian Institute of Marine Sciences provided us with this. You all have this folder in your maps folder that I shared that has this SHP file here that is a shape file, including all the islands and reefs along the Great Barrier Reef. So the reason why I wanted to do this exercise is for you guys to realize that depending on the scale that you're looking at, you're going to need a better resolution app. So let's do that now. Go to script 4. And this one I might go a little bit faster because I'm assuming you know the steps that I'm doing. I'm not going to do anything revolutionary here, not going to do anything new. But the thing that, oh, wait, just a minute, pause. I did add the piece of code here to plot Lorenzo's pizza using the Robinson projection. So how do you find a point? Just pause on Lizard Island for a second and come back here. How do you find a point when you're using a certain projection? This is how. So I created a point that is a data frame with the coordinates that Lorenzo gave me for where to find the best pizza in the world. You have latitude and longitude, so you know where to go. But that is just a normal data frame in R. The first thing you do is you transform that to an SF object using this function that's called STSSF from the SF package. And then you give it the coordinate reference system that you want to use, which is the same one. You can just copy and paste from the world. So if you call world, you can just come here and copy and paste this bit here into the projection here, because you want it in the same projection, right? You want it to be in the exact same projection as the X and Y coordinates, so you know where it is. So your PT is now an SF. And look at the geometry. It's a point instead of being a multi-polygon. And the difference between a multi-polygon and a point is that a point only has 2 coordinates, X and Y, which we gave it on the data frame. Once we created that point, we then transformed the SF object to a Robinson projection using the ST transform, which was the exact same function that I used to transform the map of Italy into an Robinson projection. You use it to transform your point, and then it will give you that projection. The geometry turns into a Robinson projection. So these are your now X and Y coordinates using the Robinson projection. Now you can plot your map of Europe with that point that we just created. Bear in mind, instead of using now geom point, because this is an SF, we use geom SF again, but it's a point because the geometry is a point. Does that make sense? And there it is in black, the pizza place that Lorenzo loves. Cool. If you haven't had time to copy this line of code, I can email that to you afterwards, because this can be quite important. If you want to use a projection, which is fair enough, you need to know how to transform your points. And this is how. Save. Good, good. Lizard Island. Let's get to Lizard. So loading the same packages. We don't actually need the Ggplot on your packages there. I did load the Ggplot, but then I realized that the function that I was using was not from the Ggplot. So we won't need Ggplot anymore. Ggplot does composite figures in Ggplot, just so that you know. If you want to do figure A, one graph, figure B, another graph aligned, that's what Ggplot does, but there are other ways of doing that. But cool. The difference here, as I was telling you, is that we don't have enough resolution in the world map to show Lizard Island because it's a tiny island. When we decide for a lower resolution, we lose that kind of resolution. So you can use the stRead function from the SF package to read a shape file. And here I'm only giving you the direction to where that file can be found. Again, if you are using a Mac and if you have the map saved on your desktop, you don't need to change anything, but you need to change the directory for that, just to where your file is. Are you okay with that? Do you all know how to do that? Cool. So once we read this, which you're gonna be familiar with it, it's almost like a read CSV in which you read a data frame. But this is an ST. Your reading is a function for reading shape files. And then the class of that, if you run, it is, again, an SF and a data frame. That's cool. So instead of now using the world, our world object, now we have a different object that is called GBR data that I downloaded from Ames. And if you look at it, it's the same structure as the world, but now it has 9,612 features, which means 9,612 what? Polygons and 35 fields. So it's giving you 35 fields of data associated with each of those polygons. So for example, and the rest, it's again, dimensions is showing that it is on a X and Y coordinates. It gives you the bounding box and it tells you the CRS, which is, you can Google later what this CRS is, but it's a very similar one to the GPS one. Anyway, but because in this data set, we have so many features, so many polygons, this data set is very heavy. I decided to filter some things. And because it is a data set, you can filter it the same way using tidyverse. Just filter things you don't want. So for example, I just want features from the GBR because this also has features from the Torres Strait. But just for the purpose of filtering things so we can make our data set slightly less heavy, let's filter for only islands, only country equals Australia. So all of these things, dataset level 1 and country, are within our column names within our GBR data. So if I call GBR data country, country, there you go. You have probably Australia, Papua New Guinea, many places where because the GBR extends all the way to Papua New Guinea as well. But now we're just filtering Australia for the purpose of this exercise. And you can actually plot that. So now that we have, a subset, and I only want islands, this feature has islands and reefs. So I'm filtering a lot. So we went from having 9,000 something features to only having 1,000, which is more manageable. But still, you're going to see it takes a little while to plot in this case because it's heavy. Before we were dealing with 241 countries. Now we're dealing with more than 1,000 islands in the GBR. And just by using the more default plot, what we get is the whole GBR subset that we were looking at of islands in the GBR. Hopefully, someone has already ran that piece of code. It will show up on your screen, and you know what I'm talking about. There you go. Those are all the islands in the GBR of Australia. So that's what that shape file is giving me. It's giving me the contour of these polygons. And then within that data frame, it defines if that's an island, if that's a reef. In this case, we're only filtered for islands because we want to plot Lizard Island. So now you know the coordinates for Lizard Island. You can plot a map of Lizard Island that looks nice. I mean, nice, again, I think that looks nice, but if you prefer other aesthetics, now you're free to change it as you wish, because you know that this is on an XY coordinate system, and you know where to plot things, you know how to plot things, you know how to change colors. And some of you might have noticed that it didn't throw a warning for our annotation scale this time. It means the distortion of this projection is not as bad for Lizard Island. It looks like this is a pretty precise scale bar for Lizard. Or at least it has less than 10% distortion. Cool. Now, I want you to show me in this map where Lizard Island Research Station is. And Nico can finally plot your Orpheus Island. But getting to your point, now you know why we can't, like that Mauritius shape is not very good. But probably if you Google shape file for Mauritius Island, or maybe even a Pacific Island data set, you might be able to find a better one that's going to give you the coastline resolution. It's a matter of Googling and finding it. Yeah. Did you run up there? Can you scroll up, please? Did you run this bit of code? Oh, did you change the directory? Oh, yeah, you need to do that. Where did you save? Can you show me the folder where you saved? So if you go to data, no, not there, sorry, go back. TS aims NASP, and you right click on the SHP file. One of these is an SHP file. Right click. If you press this, I'm not sure on Windows. Sorry, I might run. Oh no, can you right click again? No, sorry, I'm trying all the. Oh, it doesn't work.
Are you trying to copy that file location?
Yes, do you know?
I have the same question. That's why I'm watching. I don't know how to do it either.
There is
I also can't open the shape file.
What's your working directory?
How do you know how to find in Windows the working directory?
Just get WD.
Yeah, no, but there is a way of finding like exactly the path. Oh yeah, it's here. Yeah, just copy that. Oh yeah.
I think otherwise you go to properties.
And then just change all of that.
No, change until here.
Also, if you're in the working directory, if you set your working directory, you don't actually need to put the file path. You can just put the.
Yeah, sorry. Can you delete this bit?
This?
The two first bits. And see, Windows uses a different side hash, and then that That one's fine. No. That one's no. It's okay. It's the difference between Mac and Windows. And now this one you need to change. Yes. Perfect. Try to go to the end. Try to run it now. It should work.
What's the function to set the working directory?
So no, don't run the whole thing because it's going to take a while. But just run this line. Yeah. No. So remove the C.
There'll be a tab at the top that says.
So, sorry, can I? Yeah. Excuse me. I just need to check.
You don't need like the file path.
If you do, yeah.
So this should run now.
Get WD. Oh, okay. So this is where you are.
No,
See, oh, you do need to change all the. Yeah, so it is an R thing. So if you change all of these to right hash, sorry about that. So yeah, you just need to change all of them to. That, yep, perfect. Now run just those lines. Nice. Cool. Sorry about that. You understood what it's doing, right? It's just giving the path to find the file. Cool. I might go ahead and I assume you now know how to plot Orpheus. You now know how to plot the Lizard Island Research Station. It's just a point in a map, X and Y coordinates. I hope you're all happy with it. Now, are we all good? Yeah. Now, in many instances, when you're plotting map, you want to show, for example, a region within a region. So GBR within Australia, for example. I just want to show you one option on how you do this. So you want to focus on a specific region, then put an inset in your graph. Very easy to do that. And we do that step by step. So first, let's generate a map of Australia. I'm just turning this off again because we don't want spherical geometries for now. Let's, again, download the world maps. And let's just get Australia from the world map. So now we have an object called Australia that is a SF, but it only has one feature because out of the 241 countries, we filtered Australia, right? So it only has the polygon of Australia. And then we plot that. But I changed some things in this plotting, and I saved this as an object, map of Australia. If you run map of Australia, this is the first step that I want to highlight the GBR region where it is. In a study, you could do that. So what I did was I used this geomrect, which generates a rectangle, and I made it feel transparent because I just want the outline. And okay, this is a map of Australia, cool. Outlining latitude and longitude points. So I'm giving it to this rect, X min and X max. So minimum value of longitude, maximum value of longitude, minimum value of latitude, maximum value of latitude. So Australia goes from -25 to -10. So, okay, generated a map of Australia, cool. Well, the reason why I wanted to generate a map of Australia and the reason why I did all these things here, for example, I put many background things blank, the grid blank, the border blank, everything blank, because what we want is actually I want to focus on that region where the rectangle is. So, but for this exercise, I decided to just sample from the GBR data. Now we want to plot reefs, let's say. So instead of filtering for islands, I'm filtering for reefs. And again, still within the GBR and still within Australia. But the GBR ID, which tells you the unique ID of each reef, I just use that simple function to sample 500 random reefs. Because if we're going to plot all the reefs there's more than 8,000 reefs in the GBR, and that gets really heavy. And I don't want it to take very long to plot, so I just filtered for 500 for the purpose of this exercise. But if you want to plot all the reefs in the GBR, just delete this line, and you will plot all of them. But that's going to take a long time.
You filter by latitude and longitude?
You could that, or you better than that, crop, ST crop, and then you give it X min, X max, what we did in the previous script. Cool. And yeah, just making sure they are in the same projection. So this is how STCRS gets the projection of Australia. This is how you access that long thing that defines the map projection of an object. And we want to make sure that our GBR data is in the same projection as the map of Australia, because otherwise they're going to be distorted. So I'm using, again, ST transform to transform our GBR data, sub2. And now I'm going to generate a plot that I called P1. That is the main plot that we want. We want those reefs nicely in Australia. And you might have realized that I plotted two geom SFs here. So the first one corresponds to this object chords, which is the reefs. The second one is the data equals aus, or the map of Australia. So this gray bit that represents Australia, it's in this line of code. So this is your P1. So now you can use this very funky thing on Ggplot that's called annotation custom. And this function that's also from Ggplot grob, that you define where do you want to put an inset in a graph. So now we have two plots. We have a map of Australia with all those features, and we have a map of the reefs. But we want to show where that is in relation to Australia, and we plot these two things together. This is something that Ggplot does for us. Oh, if you get that error, again, just erase this and run it again. Don't ever give up on your red letters. And there you go. What we did in this inset here, so annotation custom, I'm defining where do I want it to go in terms of minimum value of X to minimum value of maximum value of X, and minimum value of Y and minimum value and maximum value of Y that I want this inset to be plotted. So there you go, another technique for you to plot maps and highlighting a region. Cool. Does that all make sense? You can, again, save it. And in this case, I put it for saving as a PNG, which is a flat image. But again, I always save it in PDF, but I'm just showing that GGSave, you can define PNG, you can define whatever format you want for to saving your file in. Right, we're kind of running out of time. I want to get in the most exciting bit. So this next script, I'm not gonna get too much into detail in it. I want to get to the next script after this one, because this one is essentially redoing all of that, but then plotting data in maps. So all of these lines of code do things that you're probably already familiar with. Each of these polygons comes associated with data, and all I'm doing beforehand is just getting that data. For example, this is life expectancy. Life expectancy wasn't in the world. If you download NE countries, if you download that world data, life expectancy is not one of them, but there is this package called WDI that is a package from the World Bank that has a lot of data. And then you can download using WDI, using this function, and you download a lot of global data on many metrics. And you can plot that on maps. And this projection, you're probably familiar with. This is a Robinson projection. So I'm gonna go quickly through this script, but you can have a look at it at home later, and please write me if you have any questions or anything. But because I don't think this is the most important thing, I think you guys got the concept of plotting data in maps now. And hopefully everything that I'm doing here, it's gonna make sense for you once you look at home again on the script. This, I did a little exercise of plotting North Carolina with a projection to show you, for example, if you plot X and Y coordinates in a map that has a projection in it, see how distorted it is. It's completely distorted. It's just another exercise for showing if you wanted to plot a point there, it wouldn't work in terms of X and Y coordinates, right? You can kind of do that trick, but it's better for you to use the trick that I showed earlier about transforming the point to be according to the projection that you're using on your map. Then you can do all sorts of funky things. Oh, yes. Okay, this is cool. So what I did here is I filtered one of the polygons of that multi-polygon object that I had before. So before I had North Carolina, the whole thing, which is this. But what you can do is you can filter one polygon, which is what we did in Australia. We just filtered the Australian polygon. So this, we're filtering, these are counties in North Carolina. So that's what the borders are. And this is births, number of births in 1974, just to show, to give you some context. But you can plot just one county, just select that polygon. Anyway, then you can do all sorts of funky things. For example, plotting using facet wrap, which is, let's say you have data for multiple years. In this case, you have number of births between 1974 and 1978, and between 1979, 1984. You want to compare those years. This is a very nice visual way of comparing them. But the main point I wanted to make here is that this is what we call vector data. But you probably have heard of something called raster. And when it comes to rasters, things get a little bit more complicated, but essentially the difference between vector data and raster data is that vector data, it is discrete over space. So here you have multiple elements. Each element of this vector corresponds to one polygon that corresponds to a county in space. So that's limited already by your polygons. That's vector data. And each of these vectors has a data associated with it in terms of like birth, the number of births, right? So this is vector data. Raster, on the other hand, is a type of map that has continuous data along it. And you can transform things between raster and vector. as simple as using a function called strrasterize. Because this is a vector data, you can rasterize it and define the resolution you want. So this is perhaps not that important for you, but it's good to know that you can do these things. Essentially, what this function is doing is get that discrete data and transforming it into a continuous data. And it's averaging the values per grid cell that it defines. So, and we can change the resolution. So if you change the dx here, and if you put a 0.5 resolution, you're just losing resolution. So you're increasing the size of the grid cell that it is averaging from. Or you can do the opposite, which is 0.01 and make something that looks almost like the data that was before. But now it's still continuous through space. That's this yellow point here. It's not associated with a polygon. That's the difference between raster and vector data in spatial analysis. Sorry if it's getting too complex now, but the cool thing about rasters, we're going to get to it in the next script, is perhaps you can plot the most beautiful maps using raster data that is continuous through space. So what can you think, for example, that is continuous through space? Precipitation, annual precipitation, or global currents in the ocean. We have rasters for those things. Cool. This other bit here, I only put there the data for you if you want to reproduce a figure from a paper. So if we're talking about, okay, making relatively nice maps, publication quality, I'm giving you the code for the code and data to reproduce a figure from one of my papers from last year, just for you to see what I did. I'm not going to explain because there's a lot of transformation of things here, but essentially I will show the plot and you can ask me later what I've done. And the reason why I had to make all these transformations is because I was, at the beginning, I've always been very fan of using base R to do everything. So this is all using base R, not Ggplot. But what I have here is a map of the world. And again, in that case, I just wanted to show how many species, the color gradient corresponds to how many reef fish species per trophic group. Those are different trophic groups organized from the ones that have the highest concentration in one spot to the lowest. And I'm going to show you in a minute. Okay, this is the figure from the publication itself, not this one. So there you go. In the paper, the exact same thing, you generated everything through R. And those are the different trophic groups. But essentially what this is I had per grid cell in the world where there is reefs, there's presence absence data of fish species, and I categorize these species according to what they eat. And then I plotted that on a map to show where do they concentrate mostly in the world. And then by just plotting something as simple as that number of species per grid cell on a map, each one of these little points here is the center point of a grid cell for which I had data for with the number of species. So you have the scale here, obviously. And I'm giving you the code to reproduce that. So just an example on like a publication related figure using maps. In this case, was I worried about projections? Not at all. It doesn't matter for me if those points are not the right distance between them. My point was trying to show that there are more species that eat plankton in this area than in the what we call the Indo-Australian archipelago than any other trophic group. That was my point. Does this figure convey the message? I think so. It convinced the reviewers at least. So there you go. One way of doing it. But to get there, I needed to transform data because one other thing is doing Pacific-centered maps. If you notice, now our x-axis is not starting, zero is not in the middle of the map anymore. To change that, I needed to create a function that for every polygon that represents the countries, I would subtract, I would transform that longitudinal point to the place where I wanted my graph to start. So I needed to do that both for the continents that are represented in gray and for the points that are represented in colors. I'm just explaining what I did in the background. If you get home and if you get curious, now you have the code, ask me, oh, what did you do here? What did you do there? But rasters. We're getting there. I know you guys are tired, but let's make some nice figures now using rasters. We finally get to the final script of the workshop. And this script might cause some errors, but we know how to solve them, right, Lorenzo? Because now, in this script, we start playing with things, for example, like this SDM predictors. If you have not heard about this package before, if you have not heard about it, and you work with geographical things, you should be aware of it. This package provides lots of data on environmental variables. So lots of rasters of environmental variables, both in marine and terrestrial systems. And I'm going to show you an application of that here. So cool. There are other packages, for example, raster, that is important for dealing with rasters. But the first step is always the same. So we have a world map. We know now that this is an SF and it has some data frame, some data associated with it. But now, all of these bits of code here from the beginning there till here, we are essentially downloading from the SDM predictors package the data that we want. And the first data that I want to plot for you, it's a data about surface current velocity in the oceans. So all that I'm doing here is to get from the list of rasters inside that package, filter the one that gives me the current data. And this should, in theory, work. For me, if it doesn't work for you, one way out of it is don't run the options line. If you comment the options line, it should run, but it will take a while because it will download what this package does. It is like you give it a code. Oh, I want this raster. It goes on the internet, downloads it for you, and loads into R. But then you have to give it a folder where to save that raster because rasters can be quite large. If you're going to see the current one is like over 50 mega. And we're not even using a very good resolution on that one. But it downloads it. If you don't specify the folder where you want to save it, then it saves on a temporary file in your computer. As soon as you shut down your R, it will get deleted from your session. Whereas if you specify the folder where to save, which is what this options line here is doing, it will save on that directory. And I've already given the rasters for you, so it should be able to load. But for some reason, it's not loading. So if you just comment that options here, you should be able to save the raster in your temporary folder. It will give you a message. It will take a while. It will show downloading. Have you guys got there? Anybody? Were you able to download that? It spits an, there you go, a warning. And what this warning is, no, it is not, it did not work. Open R again.
The only way I got it to work was in the folder that you provided us. There's already that file. So I just use raster function to read that raster in.
Perfect. That works as well. Did it work?
I wasn't actually trying to do that. I was just watching because I got a little behind. I was just trying to keep it. I wanted to see if I could add points to this.
Well, okay, I'll get to where. Yeah, maybe it's better to just.
Myself more sometimes if I try to.
Yeah.
Follow along too fast.
Yeah. Well, you all have the code now, so you can sit down at home with time.
Quickly write the other option to get the layer into R.
Yeah. So, do you want to do that? Oh, not here. Instead of setting options, you can, as Lorenzo pointed out, velo, it's going to be equals raster.
Yeah. Probably need to load the package or install it. We probably need to load the package as well. We have
it is loaded. Okay. Yeah.
And then just
the path.
Yeah.
So
maps.
Yeah, desktop maps, and then the name of the file, right?
Yeah.
Which is this. So what a raster is, just out of curiosity, it is a TIFF. It's a photo from which you can extract all that data, because every pixel in that photo has data associated with it. That's what a raster is. It's a continuous data in space. So is that it, Lorenzo? Yeah. This is the alternative if you want to load the raster, which I've already provided in your data set, in your folders. Great, thanks for that, Lorenzo. So now, if we all have this velo raster, let's look at it. It is a different class. Remember, we were dealing so far only with SF. Now we have a class raster stack. So class velo, which is the object, it's a raster. So now, if you want to plot that raster, it's as simple as you define a color palette. That's what I'm doing here. And you just plot. Ooh. Oh, yeah. I need to crop. Oh, and what I'm doing here is, you've seen it, I want to crop exactly where the Indo-Australian archipelago is. Right? So I'm giving it X and Y coordinates, and I'm cropping my raster to that specific square. Then, just because I don't want to have a world data on currents. Just to give you an example. So, geez. Why is it not? Yeah, there were some package problem that it's not plotting. If I load maps, maybe. That's annoying. Anyway, never mind. This was a quick visualization. Probably there's a conflict in the plot functions between some of the packages I loaded here. Maybe raster should be loaded before maps. Because the order that you load your packages, if there is a conflict between them, say you have two functions called plot in two different packages, the one that you load second is the one that's going to be used in our. So that's one way of solving it, but that's okay. This was just a quick visualization here. And what we want to do in all of these things is, this is giving you the resolution of your raster in terms of, I think is square kilometers or something like that, or anyway, the resolution of your raster. You're defining a coordinate reference system. In that case, we're using the traditional long and lat. And all this is doing is just generating a data frame that was extracted from the raster with latitude and longitude points with a value of mean current velocity. And if you plot that, finally, using things that you've already learned, what you have is a plot of a raster with mean current velocity. It takes a little while because it's heavy, and there you go. This is the reason why I think rasters are so pretty, because it's continuous in space. As I said, it's a photo. Every pixel has a data associated with it. So yeah, it's really cool. And all in R. I didn't have to download anything from the internet to plot this figure. All in R. And finally, I did something similar, but now for the terrestrial people. Downloaded some stuff from the.
Is there a list of these data sets that are available?
Yes, yes. So I had to rush through this. Sorry about that, but
Probably in the package.
yeah, if you just list data sets, it's going to give you all of this. And the most important thing to look at is like, what's the data set code? There's the world claim that is terrestrial. World claim has climate data. BioOracle, which is the data that I use to plot this current data. It has lots of marine stuff. MarSpec, there's even freshwater raster data that I haven't played with. And then inside that, so you can get the codes. In this case, I'm getting the codes only for the BioOracle. So these are all the layers of data. So there are 294 different rasters of things that have their own codes. If you go to the website, BioOracle has a website, you can check all these codes and things. But there's a lot of stuff in there. And what I did here, instead of getting the marine one, was I got codes for the terrestrial using the world claim data set. So the world claim data set has 68 different rasters. But the one I want is something that has precipitation on it, so rain data. So the code that gives me precipitation is this one, WC Bio 12. Then I went there, downloaded it, and now I want to plot rain in Australia. Just
Thanks for that.
no worries.
See you later.
See it. And oh, this time it worked for some reason. But anyway, that was the quick visualization that I was trying to plot before. And now doing the same steps, when you have time to look at the code, you're going to see that the same thing I did with the currents, I did with the precipitation data to generate a data frame with annual precipitation according to longitude and latitude. As easy as that. And you plot. Again, it gives you the warning about scale. And voila. As easy as that. Now, you all should, in theory, go through the code and understand exactly what I'm doing line by line because I spent so much time at the beginning explaining what each thing does. Hopefully, by the time you get here, you should be independent to, modify your plot the way you want. Right?
And a very good way to figure out what each line does is to comment it out with an hashtag and see how the plot changes as you try that. Or just change the parameters you give to the different arguments. Can you show what happens if you comment out something like scale field gradient?
Yes, this is what I did here, what Lorenzo is doing, because I wanted to show you an option. For example, one thing that I don't like about Ggplot is that it always puts the legend of the data on the side. I like to have it inside the graph. So why not put it inside? And then you can do that inside the theme. So if I uncomment these things here, I'm saying to Ggplot, I want the legend to be in this combination of, and in this case, it's not really coordinates. It's a bit tricky because it is proportion of the graph. So it's like 17% on the x-axis and 87% on the y-axis. So this position should be roughly around here. So I'm going to plot it just so that you know one way of doing it. There you go. And if you zoom, obviously it looks out of scale here, but if you zoom in, it looks well inside the plotting area. There you go. I think that's it. I'm sorry if I had to rush through the last bits of code, but I think the fundamental bits you've all understood. And yeah, let me know if you have questions or if you have trouble or if you need any help plotting your own maps. One thing that I didn't teach, obviously it's impossible to cover everything plotting maps in one morning. I try to do the most, important things so you guys can now play around with your own data. But yeah, the thing about generating your own shape files, for example, that's something that's possible to be done, but that's in ArcGIS. Again, that's completely out of the scope of this workshop. Unfortunately, I wish I could teach that as well, because that would mean you generate your shape file and then you import it in R and you know exactly how to plot that. But we would need a whole semester to teach all of this. I hope you guys enjoyed. I hope this was helpful in any way, and I'm always available for help. Any questions, any suggestions, any feedback, more than welcome and open.
Thank you, Ali. One final rant, in case you guys are not aware, we have a Slack channel that's pretty active, and it's where we go when we're trying at our code not working. I'll send it via email, and I put it on the Zoom chat as well. Feel free to join, and there's people with knowledge on using R to genetics, using Bash, using Python.
And you can try these later, and
That's
if
nice.
your map's on course, you can come and ask us there. And you can also be up to date with the courses. we're gonna be doing.
Yeah, because when I said
Thanks for coming, everybody.
Thank you.
Cheers.
Thank you, Zoom people.
Thank you, everyone. Zoom.
Bye,
and
Karen.
Cairns. I hope this was okay.
No, it was good. Thanks, Al. It was good online as well. Good job, man. Cheers.
Thanks a lot.
NetCDF is basically I'm trying to use the finance projection from CX6 and the whole on NetCDF. So this one I'm trying to compare the next situation on our to basically have I would say zeros in a and there would be like
That's one thing about spatial analysis because so many things have been developed outside R. R is actually just catching up now with the spatial stuff. Like until very recently, all the instructions R was not a tool for spatial analysis at all. So many of the things are GIS. So I assume that I've never heard of that format.
only the
I'm not sure of the.
Is it a shape file?
So basically it's an array, it goes in space and time.
I like curious form.
Even lateral and longitude, it's not XY, it's like XY, XY. It's somewhere in space.
Oh, because there's space and time.
Yes. Right, so if you never done.
Sorry.
No, it's okay.
Yeah. I'm not sure if we can do that or not. No problem. See you. Good luck with your own stuff.